Good morning. Uh, we are in the day 6 of this GIAN course on combustion theory and applications. Till this point of time, we covered up to the laminar premixed flame. Now we are going to look into the other category of flame, that is laminar diffusion flame. Now, where we encounter this kind of flames, because when there is not premixed air fuel charge. So, normally what happen in some cases, we get a kind of a laminar premixed flame, but once it interacts with the surrounding air, the flame also takes oxygen from the outside ambient. In such cases, it generates a different kind of flame that is called as laminar diffusion flame, because the fuel jet tries to diffuse the outside ambient air environment and try to generate this. Next thing, where we get such kind of situations that we have this laminar diffusion flame is, you can recall that when you look at combustion in the compression ignition engines, we spray a fuel jet through an fuel injector into air which is already at elevated pressure and temperature in the cylinder. So, in that case, the fuel droplet is in droplet try to mix with the outside air or air inside the cylinder and try to diffuse into it. Through this diffusion process, we have different category of flame, and this diffusion process leads to many number of flames, because the fuel is auto ignited, and since there could be n number of flames which can be generated at various locations of the engine cylinder depending on the equivalence ratio. So, under this heading we will try to analyze some of the topics like laminar jet. Normally, when these diffusion flames are formed when you spray fuel jet into air. So, a typical situation would be that combustion of fuel jet in an auto ignition of fuel jet when it sees the air. But to simplify that analysis, we are looking at a situation what we call as a non-reacting laminar jet, because when the combustion happens, we cannot see the main fuel and air, rather we see the combustion product. But to simulate them in analytically, we can do this with an ideal gas analysis, assuming the fact that fuel and air are mixed and they provide a jet which is typically which we call as non-reacting. But the end results or trends that we get out of it, we can extrapolate it in a combustion environment. But we do not have luxury to have analytical equations when combustion is happened, and using that combustion product we cannot frame this analytical equation. That is the reason we make these assumptions to be non-reacting laminar jet. We are doing same thing, but at this combustion product side we are assuming that the fuel and air, they remain as it is and they do not create the products. Products means we are basically looking at the mole fraction which remains at the reactant side and product side to be same in this air fuel mixture. Then by doing this, we can frame this mathematical description for the jet flame, and this mathematical description of jet flame gives the understanding the laminar flame structure. Here I mean that when the jet comes out, it talks about what is its initial momentum, how fast, how long it can go, what is the jet characteristics, how far it can spread, all sorts of information that we can get. So we call them as a laminar flame structure. Then we will in my previous discussions, I emphasized the word conserved scalar, and since it is a diffusion flame, and we are saying that there would be the equivalence ratio of fuel and air could be can vary drastically or from with different values, but what identity of fuel remains same of carbon or hydrogen, that part within that jet flame can you quantify, that is conserved scalar. So this is nothing but we are looking at the term called as mixture fraction F. Then these studies will help us to understand these heterogeneous combustions that commonly happens in a compression ignition engines. So in your earlier discussion of IC engine, we only emphasize that how combustion happens, but in these things and what happens and what are the different kind of structures that we are going to achieve, but how that shape is supposed to achieve, that we can get through this description, that is laminar jet flame mathematical description. So what is, I mentioned earlier some of the important parts of this non-reacting laminar jet. Now when you say non-reacting laminar jet, normally the classical device that can give you range of flames is the Bunsen burner. By controlling the air fuel charge here, we can regulate the air fuel mixture, and the first type of flame which you get, this inner cone, which is a pre-mixed flame. Now if you do not give sufficient charge, only fuel, then this fuel can come out and it can diffuse with outer air atmosphere, and then it can create an outer cone, and that is not through this, rather diffusion of fuel into the outside air, and we get this outer cone, that is a diffusion flame. Now how it can come as a jet? Now when it can come as a jet, because if you give sufficient momentum to this charge, so it can come as a jet, and this what you see, this particular structure, it will not remain as it is, it can travel much fast to a longer distance. We have a jet which goes, that is normally it happens in the IC engines. Now here the typical study for this kind of things, you see here in this combustion chamber where we have fuel injector, and when it is when the fuel is sprayed into this combustion domain, it comes as a jet, and when it comes as a jet, it tries to spread, and once one point is we have, and this is first set of flame. Second set of flame that can happen as a consequence of the first set. So that is what the phenomena of auto ignition is all about. So those kind of events we are trying to simulate. So initially it is a static flame which is we get in the Bunsen burner. Now when you have a jet, that we can say what you get in the fuel injector for a CI engines. Now what we are simulating here is a similar kind of phenomena, that fuel comes as a jet with some diameter of 2r, and it tries to mix with the outside air. But one assumption is that when it mix, it is just a fuel air mixture, and when it comes with certain initial momentum which is at location x is equal to 0. Now, when it comes as a jet, it covers an axial distance x, and depending on the strength of the jet, its effect will be felt at some location, and since it is coming at a free coming to the air freely, there is no physical boundary just after this location. So, what we say, it is these two jets are the two limits which we call as free boundary, and which means that effect of jet is limited within that boundary. Now, when it comes out, if you look at each plane, we have two possibilities that and the flow is axial along this the central axis, and there is a radial variation which is r, and that is your axial variation which is x. So, the starting point both the cases is x is equal to 0, which is just at the nozzle exit, fuel nozzle exit, and this initial cone, which is the inner cone, that happens to be distance x c, which is the initial cone. After that, it try to spread with the outer air. So, this is the inner cone x c, and what we are going to see here is this. So, basically there are two parameters needs to be evaluated. First is velocity of the jet, because since it is a jet, if you look at pure fluid mechanics point of view, as if it is not a mixture, then it is like a water jet, or you can say air jet. So, it is a only fluid mechanic point of view, we can say that we can find out the velocity at different x, also with different r, that means radial variation and axial variation, and that can be normalized with respect to its initial strength. The initial strength of that jet is limited by the velocity at x is equal to 0. So, what we are going to plot is initial velocity is b e, and we are looking at a parameter, this ratio at any x r is equal to 0. We are looking at x at r is equal to 0. So, and this is what fluid mechanics point of view. Additionally, in this case, it is not a free air, it is a air fuel mixture. So, that is what we have this mole fraction YF or mass fraction YF. So, if you try to plot it, so initially it start with a with its own strength value 1, and once it goes after this initial core, it tries to decay. So, this plot talks about how, what is the at different x, what is the value of V x 0 by V e or and Y f. So, this is the domain which we are looking at. This one what we are seeing is we are looking at each x 1, what is this radial variations. So, we are at each x 1, we are looking at what is this radial variation. So, this plot talks about it, and this is another x 2, means far downstream of this. So, mole fraction which was initial at x is equal to x 1, it further down, and this is the location at r max, which talks about this maximum value at this location. So, then next step is that now what is the fundamental behind this? What we have is that we have a potential core. Second, we have the presence of viscous shear. Third, effect of diffusion. Okay. So, in the potential core these defects are not felt, and which is somewhere in the initial domain. But when it comes out, particularly in the inner cone, when it comes out to the, when you move towards the outer cone, all these effects comes into picture, and we are going to analyze that analyze as if it is a nozzle fluid interaction in terms of mass fraction and the velocity fraction. So, those analysis we are going to carry out, that at any x or any r, how do you make your judgment, what is the, what should be trend of the profile. So, most important the thing is that there is an initial jet momentum which is conserved throughout the flow field, and the jet, as the jet penetrates with the surrounding air, the jet momentum is transferred to the air. So, thereby the velocity decreases, and the greater quantity of air that are entered into the jet are carried away by the downstream. So, when you look at this typical nature of the profile, this profile appears to be in the decay. It is called as a decay of the decay in terms of velocity and mass fraction of the fuel, and that is decay is both in radial direction and axial directions. And we see that at central line we have this maximum effect, and in the once you move away from this central line, its effect will come down. So, the beyond this potential core, radial velocity decays from maximum to 0, which is from central line to the edge of the jet. Central line is this, and edge of the jet is this. Suppose you look at this particular plane, we have the central line point and the edge of the jet. That is what these notations are there. Now, we all know the Fick's law. Through this Fick's law concept, we can quantify the concentration of the fuel when it spreads through this diffusion term. Now, next point, important point is the effect of moving downstream into the downstream is to increase the time available for diffusion to take place. So, it means that when you go downstream, means jet has enough time to mix with the surrounding air, because it has a wide range of domain of air entrapment. And so, the width of the region containing the fuel molecules grows with axial distance, and central line fuel velocity concentration decays in a similar fashion as that of velocity. So, basically effect of fuel and air concentration, they follow a similar pattern. So, these are some kind of standard mathematical treatment. How do you go about it? So, basically this is a case where it is a radial coordinates environment or cylindrical coordinate environment r and x. So, terminology that I mentioned here, that initial point which is at x is equal to 0, and at this point it is center point which is r is equal to 0. So, that is the starting point, and that r is equal to 0 line we have this x plane which is x is equal to 0. First, potential core stands with a distance or standoff distance which is xc, and this xc talks about the peak point of this initial conical potential core. And when the jet spreads, there is a partition. So, partition means we call this as a jet edge, which means that these are the imaginary partition, because there is no physical partition. These are the imaginary partitions that separates completely atmospheric air outside and the fuel air mixtures. So, basically in this domain what you see, that air fuel mixture of various strengths. Some zones will have a high equivalence ratio which is towards center line, some zones will have less equivalence ratio when you go towards the edge, and that happens at any x as well as any r. So, this is the terminology that we use in terms of jet edge. So, what we are trying to find out is that what should be the if you solve this kind of fundamental problem in a cylindrical coordinates, what we are trying to look at, the concentration of velocity and concentration of fuel at various r and various x. So, we are finding out a general fundamental correlations that can cater both. So, the solutions for this problem lies in taking care the mass conservation equation in a cylindrical coordinates r and x. Then we have this axial momentum conservation, because the effect of jet is only in the axial directions, that is momentum equation. Now, in fluid mechanics term, these two equations are sufficient to quantify velocity, but in combustion viewpoint, since you are looking at fuel species, so you have to find out the species conservation equations in terms of its mass fraction. So, here there is a term called as d, which is known as the diffusion coefficients, and this d, effect of d, we can say that how we can find this d through Fick's law, and these are the governing equations, and we are trying to solve with certain boundary conditions. First case is along the central line of the jet, which is r is equal to 0. So, at that case we have the velocity rx, vrx, and for this the Vr and Vx, V is radial velocity, Vr stands as the radial velocity, Vx stands as axial velocity at different x. So, these notations tells you that what velocity we are looking at. So, at that location your dV by dVx by dr is equal to 0. Again similarly we can find for fuel fraction also. At large radius means if you go far away, at large radius fluid is stagnant where no fuel is present. So, this is the condition of Vx and this is the condition of mass fraction of the fuel. Another study we can another things as a boundary condition you can say at what is happening at x is equal to 0, means in this plane x is equal to 0, we can have r is less than or equal to 0, r is greater than 0, greater than r, small r is less than or equal to r, r is nothing but the diameter of the fuel nozzle, and that r can also be greater than 0. So, this value stands as 0, but at any value it all depends what is the fuel mass fraction at that location. So, with these boundary conditions, these are the main equations, governing equations. Second set, these are the boundary conditions, and another point is that we can calculate the momentum the flow of the jet at any x by considering its density, velocity along x directions and r. So, if you find out that value terms as rho e v e square into pi r square. So, that is nothing but your initial momentum, which is at x is equal to 0. Rho e and V e stands as the velocity at the exit of this nozzle. Rho e is the density of the at the exit. Density means fuel air chairs combined density. And fuel mass, this is the momentum. Also you need to find out the fuel mass. So, same term is here, but with an additional term y Fe. I think there will be square here. So, there is an additional term with fuel mass. No, sorry. Because this is mass, fuel mass, then this term is momentum. So, it is a mass term and this is a momentum term. Okay. So, the solution lies in the fact that it has to be solved in a particular fashion, which is similar to a similarity through similarity parameters. Those concept of similarity parameter was introduced when you talk about the solution of flat plate theory through Blassius equations. So, there we introduce a term called as similarity parameters. Here also we are going to introduce a similarity parameters, because those complicated problems involving R and X and then finding combining all of them, because we need to analyze fuel and air fuel parameters in terms of its mass fraction. Additionally, we are also finding the velocity term. So, both the things has to be combined in a single loop, and those things we are going to look at how they vary along R as well as X. So, similarity index zeta is formed for its solution, that is zeta. So, it is this zeta takes its initial conditions which involves this jet momentum at this initial stage Je. Rho e is the density at the exit of jet, which of the air fuel charge, and this and also it is taken about the viscosity part mu. All these terms combined in a particular manner with a ratio R by X. R stands as radial direction and X stands as axial directions. So, this is a very unique parameter which depends the initial condition of the jet, fuel jet, which is just at the exit of the nozzle, and this. So, one interesting part is that this similarity parameter is it's a common term which can be used for calculating the velocity term as well as the velocity decay as well as the full mass fraction decay. Now, through this process, how the equations, all those governing equations, when it is solved, it turns out to be a fashion which is called as non-dimensional axial velocity distribution, which is Vx by Ve, and where this is expressed in terms of Reynolds number, in terms of the ratio of x by r. Again there is a term zeta, this similarity parameter we drops in here. So, entire terms here are non-dimensional. This is ratio. So, this say that how the velocity decay takes place with respect to its initial velocity just at the exit of the jet with a function of x and r simultaneously. That means, if you are fixing x and trying to find r, so that is with respect to x, Vx by Vx, and r is the fixed number, which is the twice r is the diameter of that jet, fuel jet. Now, through these things we can find out similar term which is fuel mass fraction. Interestingly, this ratio and this ratio bears same value because it is a ratio. Now, coming back to central line velocity, at central line velocity we have to find at r is equal to 0. So, when you put that we get out of this number and we have this central line mass fraction as well. So, along the central line this value remains as it is. Okay, this is how we find this jet characteristics. But one particular condition is that these solutions are valid when your x by r is greater than 0.375 RE. This is the minimum location where x by r can valid. And Cummins number, which is the ratio of mu kinematic viscosity to the binary diffusion coefficient, is equal to 1. Why it is say? Because we are assuming this jet to be non-reacting, otherwise this will not be 1, because we will have a binary diffusion has a fixed value and a certain value when we are introducing the diffusion coefficients. So, whatever analytically we say, this can be represented in a graphical manner just to take care about the study what is the Reynolds number effect. So, if you are increasing the Reynolds number, we see that the dimensional central line velocity increases, and at a given Reynolds number, if you are increasing axial distance, the central line velocity drops. So, that means there is a velocity decay. A similar trend is also true for fuel mass fraction decay. Another important parameter which is of quite interesting is to find the jet spreading rate. So, jet spreading rate is a concept we are looking at, that we define a parameter which is the jet spreading rate and spreading angle. To do that, we have to first find out jet half width. So, jet half width is defined as the radial location at which jet velocity has decayed to half of its central line velocity. So, we find a parameter r half by x. So, when you say this decay, correspondingly we can find a spreading angle. So, what we are looking at is that when the decay at any x, when you are looking at if the jet has the ratio of the radial location at which jet velocity has decayed to half of its velocity. So, radial location is in this manner and it decays to half of the velocity, and that distance is x. So, that is the location what we call as jet spreading rate, which is r half by x. This is one part, and when you say by solving that equation, this turns out to be this number. It is 2.97 times R e to the power minus 1. Now, when you define this jet spreading rate, then we can find out jet spreading angle. So, this angle R half to this x is known as the alpha, what is called as jet spreading angle, that is tan inverse R half by x. And here this Reynolds number stands for this Reynolds number value stands with at a location which is R half, that is jet half width. So, it says that this analysis says that at high Reynolds number jets are narrow, while low Reynolds number jets are wide. That is quite natural, that is initial state. During the initial phase the jets are narrow, and when the when it is spreading or at low Reynolds number jets are wide. So, through this analysis gives us some kind of generic features for a laminar diffusion flame structure. So, initially it was a jet, but one can say it is not actually a jet. If it is actually a fuel air mixture, the typical trend could be like this. So, instead of spreading at this, we are looking at a domain where this effect of fuel is there. So, what we see here is that this is the twice R, which is the diameter of the fuel nozzle. At x is equal to 0, this fuel air mixture starts to spread, and we are looking at x. And when you talk about this very specifically, this laminar diffusion flame, for example, when you say pre-mixed laminar flame, when you create a spark, a flame is created, which is nothing but a imaginary region between the burnt charges and unburned gases. That is what we visualize. Similarly, when you say laminar diffusion flame, we say that we can have a imaginary domain or shape or a trace that actually specify two regions, which is fuel rich area and which is fuel lean area. So, that shape, that is called as phi is equal to 1. So, that is the zone which separates two regions, which that is called as a flame zone. It separates two regions, one is rich fuel, other is the lean fuel. So, below this line it is a fuel rich, above this line it is fuel lean. Again, although it is rich zone or lean zone, but one interesting thing, what happens in that axial distance. So, axial distance also, this richness or lean, that value varies. If it is a rich region, that value varies. So, that means initially if you look at rich region, it is of very high strength, and as you go towards the flame zone, it becomes leaner, and at phi is equal to, stands as phi is equal to 1. Then beyond that line we are moving towards lean regions. Similarly, if you go far away, we can have this effect, but beyond this point, this we can assume that it is the effect of fuel is not present. So, we call this as a far field regions. So, in this domain it is completely air. So, this is one kind of flame structures that evolves out of a jet, and we try to model them in this manner. So, the flame structure which is defined, phi, which is R is equal to, or in particular we say laminar flame structure, which is phi R is equal to 0, x is equal to LF. That means this flame length. So, x is measured from here. So, at this location your x is equal to LF. So, this is the this is how we define this flame zone or laminar diffusion flame in terms of R and in terms of x. That means that is the maximum x which can have, which can fill that flame can fill with equivalence ratio of 1. And other points I have told you already. The fluid and oxidizer is consumed within the flame which is at reach, and the products of compositions have strong correlation with respect to equivalence ratio. Flame surface is normally defined as a contour where fuel and oxidizer meet at stoichiometric portion, which means that if you look at any point on this flame surface, the fuel air mixture is stoichiometric. This is not at a point, this is a surface. In other words, the flame surface is defined as the locus of points where equivalence ratio is unity. In some cases, we say it is a over ventilated flame where there is more than enough oxygen for the oxidizer in the surroundings to burn the fuel completely. So, that means some cases when you have additionally, normally in the diesel injector there is a direct injection, there is indirect injection. Direct injection normally comes out, but still we pump indirect injection, that is normally happens in small engines, small CI engines. Larger compression ignition engines have enough space, so that way we get the flame structure of like this. But small engines, it does not have enough space, so we give additional fuel in a different route. So, the initial flame is not called as the flame surface. So, we can say it is a over ventilated flame, but with an extra air oxidizer. So, through this concept, what we can find out that because there is a quite significant variation of equivalence ratio from phi is equal to 1 lean to reach, there are possibilities that the sum says in some cases the flame becomes narrow and in some cases flame becomes wide. So, narrowing the flame increases the fuel concentration gradient, that enhances diffusion, and those cases, because those cases why it is happens, because buoyancy accelerates the flow. So, the flame length which is stands as LF is decided by these two phenomena. Okay. That is another kind of events that we get in laminar flame structure, which is typically called as soot formation. Soot formation as well as soot destruction. So, what you see is that after solving this, we get some kind of shapes. Now, why this soot particle forms? Soot particle forms because we are not, it does not find sufficient air to combust the fuel particles, and the carbon which is there in the fuel remains as small particles. Now, where is the location that soot particles can form? That can form only when we are in the within this dome, rich mixture zone. So, that is the zone where if it is, since it is an auto ignition event, not necessarily that every corner of the combustion domain the fuel air mixture will be equivalent. This is one case where this is one zone. If there are multiple fuel injectors, so there will be combined effect of all the fuel diameters. So, that way we cannot precisely say that whether soot particles form or not, because it is the combined effect of pressure, temperature that decides an effective combustion zone. So, let us say in a combined effect or situation the soot particles has to form. and it normally forms where there is a fuel rich region. So, the first layer of this fuel which is called as soot particle inception zone. Now, these soot particles grow in sizes. Initially it is a small droplet, and because it grows in the sizes, and they started oxidizing, because when they go to the outer core they see enough air. So, it is not combusted, but it has moved to it has diffused into air. So, when it starts, initially it starts with soot wings and then soot breakthrough. That phenomena is typically called as soot formation or wings, and they finally break down. So, when they finally break down, we call them as a smoke. So, this process talks about how the soot formation, how it then finally evolves down to smoke. So, it started with the flame tip region and boils down to smoke if they are not combusted properly. So, this is a quantification for this flame length LF, and which is for a diffusion flame, simple relations. How do you find this flame LF? Through our analysis, through our laminar flame, non-laminar diffusion flame analysis, and it is a function of two important parameters: initial velocity, initial fuel flow rate, its mass fraction at stoichiometric mass fraction, and where initial fuel flow rate can be related with the initial condition with respect to its area. Next point I need to tell that how that similar concept which is actually designed, that if you need to this particular term talks about three things. One is as if the combustion has happened, and we have fuel and air, oxidizer and the products. So, there are, for each case, fuel has its mass fraction, products will have their mass fraction, oxidizer will have mass fraction, and this is nothing but as a function of F. F is called as the mixture fraction, which is correlated to the species mass fractions with fuel, oxidizer and products. So, that definition I have given in the previous lecture. So, we are looking at this F, which has a stoichiometric value, and in this zone this F value is within the less than 1, and this is the flame sheet. This F value is stoichiometric value is this side. So, basically in this zone we are trying to find out the fuel and products. Here there is no fuel because we have already crossed this flame sheet zone. So, we have only oxidizer and products, and on this flame sheet we have this only products. So, as if on this flame sheet entire fuel air charge has combusted only in the products. So, along this X we are trying to see the various value, how the temperature drops from within the flame and outside the flame. This particular curve talks about state relationship species for mass fraction, and this is for mixture temperatures. Now, coming back to exact calculation of this mixture fraction, by definition we say this. So, from this one can correlate this mixture fraction as a function of your fuel fraction and product fraction, mass fraction. And remember, these are the mass fractions, this is the mixture fraction. Mixture fraction talks about only the mass of material which originated from the fuel stream, MC and MH. And normally when you solve a generic version of diffusion flame analysis, we solve this kind of equations which talks about what happens inside the flame, what happens outside the flame, and what happens on the flame surface. So, this is all about the diffusion flame characteristics and behavior, and just to extrapolate this in a practical viewpoint and applications, we call them heterogeneous combustions, where air fuel mixtures are not pre-mixed and fuel is a high temperature air, and typically this happens in CI engines, and how it evolves down, which gives the similar correlation what we have studied here for laminar diffusion flame, is like this, that normally this mechanism we have there in the CI engines, where you talk about pressure volume diagrams, pressure crank angle diagrams, and mixture is mostly heterogeneous and defending with different normally CI engines are operated at different compression ratio, and we have fuel injectors. Their fuel is injected at a particular location of where at the late compression stroke. Then what happens after that? So, after injection the fuel undergoes three things: atomization, vaporization, mixing, self ignition, and combustion. So, through this route the fuel happens this. Now, what we are looking at in this analysis is that what happens when it fuel vaporization and tries to mix. So, in this zone whatever study we have done, we are trying to correlate. So, this is how we come from a fuel injector. When the jet comes out, it is along this axial line, it is only liquid things, it try to vaporize. So, in the next lecture we will try to see that when in the liquid region the fuel is in droplets, and that it has some initial diameter and try to evaporate. That analysis or treatment part is something different. I will come back in the next lecture. But here what we are looking at, when it comes out as a jet, what is the zones that it forms. So, first zone is A, which is too rich to burn. Second zone is rich and combustible. Third zone is stoichiometric. Fourth zone is D, which is lean and combustible, lean but combustible, but E is the too lean to burn. So, obviously we are moving from very rich zone to very lean zone, which is far stream, and the self ignition occurs at zone B. So, that is the most effective zone where entire fuel droplets gets combusted, and other zones are non effective, but when they interact with when they interact with other kind of fuel molecules in which fuel is injected at different locations, they also create similar kind of combustible zone. So, this is how the end results of that analysis is correlated with typical fuel injection in a engine. So, rest of the things is like a textbook, I am not going to detail. So, here when you talk about vaporization zone, because of its strength or equivalence ratio conditions, 90% of the fuel gets vaporized. And in the mixing zone, we have the fuel mixing takes place. This is the comfort zone of engine, where we say equivalence ratio for mixing. And ultimately, when you see this particular effect, and we expect the corresponding rise in the pressure in the cylinder as a P theta diagram, point 1 is the fuel injection, B is the fuel injection starts, B is the ignition, and so initial period there is a slow rise and there is a sudden rise from B to C, and at this point that's the gives the peak pressure and peak temperature, which is adiabatic flame temperature. After that there is a decay. So this is same thing that the fuel ignition simultaneously starts in the fuel rich zone, and typically that is zone B. Then in the combustion zone, which seems to be a zone between the path B and C, and that typically this is the combustion zone period, and normally when this combustion initiates, the average piston speed in the cylinder, which is in the range of 5 to 20 meter per second. Ultimately, the C10 number of the fuel, this is another characteristics of the fuel which talks about the effectiveness of a fuel in a diesel engine applications, because the fuel has to ignite, and if it is too low, if the C10 number of the fuel is too low, then there is a greater chance of the fuel, greater amount of fuel will be injected. So this particular event, when there is a greater amount of fuel which is injected during ignition delay time, this is the time where it creates the formation of soot, and they try to spread. Then lastly, this is a concept what we call as a direct injection engine and indirect injection engine. Normally what happens, we are looking at, for diesel engines we are looking at very in the range of compression ratio between 12 to 18 to 24 or higher. But what happens is that when you look at small compression ratio, engine cylinder, although we are going for compression ignition mode, but the ignition the area does not have sufficient for us to create an environment of environment which is favorable for combustion, because the fuel does not come as a jet for a long distance, rather it terminates at short distance, because it sees that smaller volume in the engine cylinder. So, but at larger engines, at larger size engines, high compression ratio engines, normally we prefer this direct injection. Direct injection means we have the fuel comes as a jet, it has a whatever strength it has, it can spread the way it wants. But that is not true in small engines at higher speeds. So for that reason we need to create a ambience where we can alter the jet characteristics of the fuel. So that is the reason we spray the fuel or we create some artificial turbulence, and when you have this artificial turbulence, to have this similar effect what you need to have for a higher speed. So those are called as indirect ignition engines, which means there are some which means initially there is a fuel injection, and side by side we also evolve multiple injections simultaneously. So those are called as indirect injection engines. But indirect injection engines are very prone for a uncomfortable combustion, and that is the reason diesel engines at lower compression ratio are usually avoided. So, with this I conclude, and there are some review questionnaire which talks about the just to solving the problem for textbook problems, like this particular problem talks about what is the effect of Reynolds number at various values of mass fraction and fuel fractions at different R and X. So, starting from the basic definitions of the expressions, one can find out Reynolds number at various locations and try to find out its the characteristics of flame, and of course, we also can find out the jet spreading angle. These are the some numbers which talks about how the fuel decays with respect to the expressions analyzed through the similarity solutions. So, this is also similar case in which we are looking at a problem is that in one case we are talking about exit diameter of a nozzle which is required to which is the base exit diameter, and if the what is the effect of exit diameter if you need to increase the exit velocity by 10 times. So, this alters actually the Reynolds number, and as alteration of Reynolds number the jet characteristics changes. Similar problem we try to look for in the combustion ignition engines to find out the flame speed. This expression how the flame speed is calculated in a diffusion flame in a combustion environment. So, with this I conclude. Thank you for your attention. Yeah.
Okay, welcome back to the second week of our lecture. Today we will have 2 hours focusing on pollutants and emissions. We will discuss the kinetics, of course. We have a strong chemical background here. We'll talk about the different pollutants and so on. So what are the main pollutions, especially when we consider hydrocarbon fuels? So HC, so unburned hydrocarbons, carbon monoxide, nitric oxide or NOx, sulfur oxide, we have soot, particulates, and finally, at least in our days, it's also considered as a pollutant. It's carbon dioxide, leading to the greenhouse effects. So we have a lot of different pollutants here with different effects on the environment and on the health. There are measures to get rid of these pollutions. And so we will discuss the formation of this pollutant, mainly NOx and soot formation. And we will discuss how to optimize the combustion process and which additional measures we can use to get rid of these pollutants. So when we look at the chemistry, of course, we have to consider the efficiency of the combustion with regard to unburned hydrocarbons. And we have the formation of polycyclic aromatic hydrocarbons, PAH, soot and particulate matter, and nitric oxide, nitrogen dioxide, and nitrous oxide, which we consider as NOx, and with a lesser extent carbon monoxide. So when I landed here last week, Sunday at Delhi airport, there was heavy smog already, and so this is an article I have read, so it's from 30th November this year, so just 2 days old. So quite actual problem here in India. And here the focus of this article, that's not only a problem of Delhi region, but of course we have an entire sweep to all other northern states, including Bangladesh and so on. So this remembered me when I was young in the 80s, we faced similar problems with the acid rain, mainly from nitrous and sulfuric oxide or sulfuric acid produced by coal power plants in Czechoslovakia and former Eastern Germany. So it was behind the border, so we were not able from Western Germany to control this, and we have to live with the outcome of this pollution crisis. Nevertheless, there are measures to have clean combustion in combustion engine, and there are measures to have clean combustion with power plants. However, these measures always cost money, and that's more or less a topic which has to be governed by regulation. So it has to be mandatory to avoid pollutants, and then you could be able to get also rid of this problem here. So here in classical photochemical smog image over Los Angeles due to NOx formation. So we have nitrogen dioxide, which then is which absorbs solar energy, and then NO, nitric oxide, and atomic oxygen is produced. This atomic oxygen forms ozone, and this then reacts with hydrocarbons to produce hydrocarbon free radicals, and then these form then further species which have a lot of influence, especially with humans. And finally NO reacts again with ozone to produce NO2. So especially the NOx formation here is very important if you want to get rid of this problem. But when you look at these two images here, industrial pollutions and soot from heavy duty engines is of course also a very important problem. So soot on the one hand is used in industry for a lot of different processes. But here we more focus on soot as an air pollutant. So you see here heavy duty engines, a train, a ship, airplanes, where a lot of soot is formed and is clearly visible at this black fume here. And the question now is how this is formed and how we can avoid this. So it was discussed already a little bit from Professor Sahoo in the morning, especially when he has focused on his laminar diffusion flames. So when we look in premix flames, if we use proper condition, there is no soot formation. Of course, especially in rich mixtures, this can happen, but again, if we use proper conditions, we can avoid soot formation in premix flames. In diffusion flames, it's quite complex. So depends on a lot of different conditions. It's difficult to control it in diffusion flames. Here often it's better to have measures to get rid of the soot after the combustion process. So soot is formed very fast within a few milliseconds. So, and again we start with classical hydrocarbons. So propane, for example, C3H88, sorry, and within milliseconds we get very large soot molecules, which are quite heavy. So the smallest detectable solid particles have a mass of 2000 atomic mass units. There's also then a transition from the gaseous to the solid phase. So it's a quite complex process, of course, and this we will see, and then I will try not to go too much into the chemical details, but at least I want to show you the complexity and the possible pathways we have. So either we can discuss the details afterwards, or at least you can take the slides to have some background information. If you ever face this problem in the future, you can start to look at this here before you have to find further literature. When we look at the energy part, so soot formation is entropy driven. We have a positive delta in enthalpy, but we also have a positive change of entropy. And then the condensed phase carbon forms as an aerosol. This is then kinetics driven. So there are possible different factors which supports here the soot formation, starting here from propane, single aromatic ring over this benzpyrenes, finally leading to large soot particles. So again, the scheme here, so we start with very small particles and have a lot of intermediate species here, and we have then finally the soot formation, and we can separate a molecular zone and this particle zone here when we look at the different processes. So this is a typical diffusion flame which Professor Sahoo has explained in the previous lecture. So we have a fuel flow and coaxial airflow. Then we have a reaction zone where we have optimum conditions. So here it's called premix blue flame. You can see it here. But then here in the molecular zone, soot particles are formed, and then we reach finally the particle zone where we have growing soot particles, but these are then oxidized again where we have excess air at the tip here. So this classical yellow light normally comes from soot particles burned in the upper part of the flame. So here we have more or less the formation, and then here we have the oxidation of fuel particles. So this was examined, for example, using taking some probes and looking at the size of the particles. So what we can see here, with proper flow condition, of course there is a formation of particles, so up to a diameter of 35 nanometers. And then in the oxidation zone, they are consumed. And here at a given height only very small particles can be found. If we increase then the flow rate, so change just the flow condition of the flame, we see that this oxidation process is no longer effective. So at even at much larger height of the above the burner, again bigger particles can be detected. So as I said, for diffusion flames it's quite complex to control the combustion process with the aim to avoid soot particles. And of course it depends on the molecular structure, and one criteria is the so-called smoke point. So that's the flow rate with such a flame we have seen before. So you have to increase the flow rate until the combustion is no longer efficient, so the oxidation does not consume all the soot particles anymore. So you increase the flow rate, and at a given flow rate your flame starts to smoke, and the higher the flow rate, the more the lower, this way around, so the lower is the suiting property of the fuel. So propane, simple hydrocarbons have a very high flow rate, so acetylene or toluene here, the aromatic substances, have very low flow rates. So here smoke, soot formation and smoking starts quite early. So the main background here is based on some work starting in Germany in 1965, where they used mass spectrometry, a group of Hohmann and Wagner, and so they detected polyacetylenes up to C12H2, but of course species like C2H and C4H3, and based on this work acetylene was chosen as a model substance from aliphatic fuels to produce soot. So, and acetylene and polyacetylene were the major components here, and they also find so PAH here with higher atomic mass units in this flame. So the classical setup was so we have either C1 species, we have seen it in the part of dealing with combustion chemistry, which can form in rich flames C2 species here, and of course when we have larger aliphatic fuels they decompose until they reach this C2 species. Here is acetylene, and then based on this work the formation of C4 species, finally C6 species was discussed, leading to aromatic a species which then may react with other species to form larger polyaromatic hydrocarbons. So the idea was that there is an attack of C2H on 1,3-butadiene, and this then finally forms the first ring, and with this ring structure here and further increase of 2 aromatic rings and so on was discussed. So the most important topic here is the first formation of an aromatic ring, so of benzene, and this can be either done by the way we have discussed before on the last slide, so the attack of acetylene on 1,3-butadienyl radical, or this is what I have discussed on the last slide, vinyl radical with butadiene with ongoing cyclization and so on. So we have a lot of different ways here to form benzene based on this acetylene chemistry. But it depends, of course, on the experimental condition what we can see. So we can find an aliphatic structure here. We can find very complex molecules. Here we can find cyclic molecules, and finally we can get benzene itself. So there are possible pathways here, and the question is, of course, how these elementary reactions occur on the molecular level. You can see here, I just want to show you the complexity we have to discuss. It's a very, very, very complex problem, and of course when you consider the reaction mechanisms, they have to include a lot of species, and they are quite complex. So when we look at methane, ethane and propane flames, it is clear methane flames produce most of the soot. Propane flames. And so when we look at propane, we can yield this propagyl radical, and with the others, methane, ethane, normally we end here at acetylene. So the question is then, which is more effective if we discuss soot formation. So this was the way we have discussed until now, and again, methane, ethane do not form so much soot compared to propane. So is this way eventually also of importance? So, and this was shown by Ravi Fernandez. You may know him in his PhD thesis. So this propagyl radical here, C3H3, is a very important molecule finally. So two of these molecules form one aromatic ring. So it's a very effective way to form radicals, and therefore this finally leads then to soot formation. Of course, as you see here, it's quite complex. So you have a lot of potential intermediates, a lot of different pathways. So how these two molecules, C3H3 plus C3H3, react together finally to give us benzene. And of course, we have a very complex reaction here. So, but there are possibilities to examine this in reactors. So here we use C3H3 iodide, which is then photolysed by a proper laser. So we form instantaneously a huge amount of C3H3. So here we measure the absorbance of these species. So after the photolysation, we form a lot of C3H3, and then this reacts, and with a given reaction rate, the number of radicals reduces. So with simple assumptions, we get a second order rate, so that in terms of absorbance we can calculate the reaction rate parameters. So quite simple second order fit. So we then get information about the reaction rate of C3H3 plus C3H3. Of course, there is an not only the formation of benzene, we also have the formation of this phenyl radical plus H. But this can absorb, for example, absorbance of hydrogen atoms, and here we can then get information also about these reactions. So this work then from Ravi was start of a lot of other work from other authors, so they have examined the different conditions, different pressure, mainly with shock tubes, the reaction rate of these different specific species at higher temperatures, and I think with RCMs and so on at lower temperatures. So how can we resolve now this complex reaction scheme we have seen here? So C3 H3 plus C3H3 gives benzene, or C6H5 phenyl radical plus H. So and one possibility is of course to use a time of flight mass spectrometer, where you suck out some of the molecules from the reaction zone and look what molecules you have. And this then can be continued that we have here to consider different routes here, so they call it even route, so where molecules with even number of carbon atoms reacts. So this is the way from Wagner, so acetylene plus C2H forms an C4 radical. This then reacts again with acetylene and we get this phenyl radical, or following this C4 radical plus acetylene gives us benzene. And then there's the odd route, CH plus acetylene gives propyl radical, and this then can react with other species finally together here, or with itself, C3H3 plus C3H3, either phenyl plus H or benzene. So we have seen from 1965 until today a lot of work was necessary to extend here the mechanism. So now we are at the stage of benzene, but this is of course still not Soot. So how do we yield then Soot? So first of all, question is how these cyclopentadienyl radicals, mainly based on fulvene here, can form also hydrocarbons. But again, you see this is quite complex. I do not want to go here into the details today. So a lot of different reaction routes are possible. And of course, this is quite a complex scheme behind this. But this is then part of the way to form higher hydrocarbons, here naphthalene. Again, based on this the complex reaction coordinate diagram. So first of all, 2 cyclopentadienyl may form these naphthalene, and these species here can form higher hydrocarbons. So we get an increase in the number of aromatic rings. And here I do not want to discuss too much, but of course we can look at phenyl radicals leading finally to naphthalene, and we can look at benzyl radicals leading finally to naphthalene. So we cannot discuss all the details here. So I'm lost here, and I think you may be lost here too. This is just to show you how complex this is. So, but nevertheless, so we have started with, for example, propane, and we are able to use proper mechanism at this stage to calculate the formation of naphthalene as a quite larger aromatic structure. And then this molecule reacts with other species. Finally, then we get this benzpyrene here. So we have already 4 aromatic rings, or here in this example we have 3 cyclic rings. So we are able to calculate, simulate in the molecular zone nearly all steps today using proper reaction mechanisms. So most of the processes are well understood today. So just here some details. So these phenyl radical here can react with acetylene, form this intermediate species here, and this then can form this naphthalene radical here. We have finally then on a minor root also naphthalene. So all the elementary reactions here are well understood today. And then starting here, this was the end product of the dominant root of the last reaction we have discussed. You can see how the formation of larger hydrocarbons can be described. So we have a lot of different reactions. So here's again another route how the possible growth of larger hydrocarbons can be described here. Benzene reacts with phenyl radical reacts with benzene, forming this species. Then a radical is formed here, where again acetylene can attack, and then finally an additional ring is formed here, which then again can react with another acetylene molecule to build up again this benzpyrene. So we have a lot of different pathways included in the mechanism today. So we know today the formation of larger hydrocarbon structures, or aromatic rings structures, in the molecular zone. Then the question is, okay, how do these then continue to these soot particles? And one possible way is when we start here with this coronine. This can stick together based on this so-called zipper mechanism. So we call it also bucket catcher, and these so Bucky, half Bucky structures named after the buckyballs, the fullerenes, have been detected also in flames. So we already have C30H10 structures. So a lot of hydrocarbons already in our molecule. And these larger structures then may stack together. So it's clearly visible that when we look here, for example, in this mass spectra, that we can see that there are specific higher amounts of mass molecules with a mass where these two structures here, this structure stuck together with a similar structure 3 times, 4 times. So it's just a stacking of large hydrocarbon structures. There's also the idea that there is a way of an ionic mechanism. So where primary ions attack our large hydrocarbon structure, form larger ions, because of the idea is, or the argument is, that the free radical reactions are much too slow. But first of all, the data is limited. There is not enough background information here. And when we look into shock tube experiments, there were no ionic species detected until now. So it's impossible theoretical way, but it cannot be based on experimental data. So until now we have discussed a lot of this growth here, so starting with acetylene and ethene, ethylene here, butadiene, hexatriene, and so on. So finally leading us to aromatic structures, benzene, naphthalene, benzpyrene, and so on. So all these have been found experimentally, and I hope I have explained to you now in detail the formation of soot on a molecular structure. So benzene is still discussed as a major precursor for particulate formation. The reaction models identify few properties critical to benzene formation pathways. We know that the fuel structure of the alkanes and alkenes is important for the soot formation. There are different routes we have discussed here. And finally, of course, especially when we talk about diffusion flames, a lot of factors are important with respect to soot formation. So these pathways are still under examination. So here we have first work presented in 1985 from Westmoreland and Franklach. Then there was an extension here in 1992. Again, for liquid fuels from coal and oil and coal, there was an additional class which was included here. And then we have now already work from 2007. So it's still not completed. So it's still under discussion, but you see that a lot of the possible pathways are included now. So the main question is, so why do different fuels give different soot yields? So why is the smoke point, for example, so different? Gasoline 10 times more than heptane. An idea is that benzene is the trace of a soot. Propane produces more soot than ethane and methane, because here propane we have this propagyl route as an answer. And for rich premixed combustion processes, mostly small unsaturated hydrocarbons, especially acetylene and ethylene, which are known to be precursors for the formation of benzene, and so they are also precursors to soot. So when we look now at newer combustibles, so renewable fuel, for example. So we have tripropylene glycol monomethyl ether, TBGME. We have this dibutyl maleate, DBM, which are molecules which may be used together with classical diesel fuel to optimize the combustion process, or want to replace finally diesel fuel. So we have synthetic biodiesel, we have methanol, ethanol, and yet you see that the percentage of fuel carbon converted to soot precursors depends strongly on the fraction of oxygen in the fuel by mass. So methanol CH3OH has a very high oxygen to carbon ratio, and when we look at this complex DBM, you can see there is quite a lower or much higher carbon to oxygen ratio. And this, of course, and this will be discussed after lunch, has an influence on the soot formation with these molecules. So with this, I would like to stop the first part of today's lecture here, but I'm open for questions if you want to discuss some topics already right now. So thank you.
So I just want to know more about the observance time profile. So can you just explain observance time profile?
This one?
Yeah. Please. This one. Means that initial rise and then it is falling sharply. So what does that actually indicate? So
What does it indicate?
yeah.
So we have C3H3 iodide, and then we use an laser for photolysation. So we form T3H3 radical.
Okay.
This is what we see here, the formation of this radical. And then the question is, okay, we have C3H3 plus C3H3. What is happening then? So, and two possible ways are the formation of phenyl radical plus H, or the formation of benzene itself. So both ways are possible. Other ways we have seen it's quite complex. So, and the decay here of this signal is related to the consumption of these radicals in this reaction.
So A is the reaction rate here, right? A, that y-axis part.
Yeah.
So y-axis part, it's decreasing means it's the consumption of.
Yeah. So that's the absorbance here. So here
Yes.
we have high absorbance. So we have formed these radicals, and then with specific second order rate law, these are consumed.
Okay, does it indicate it takes some time for this absorbance, mean that resolution part?
Yes, so of course the consumption of these radicals depends then on the specific elementary reaction rates we have to consider.
Okay, so actually what I'm asking this one, because while we are using the sensor, so we are getting some kind of plots for the temperatures also. So does this observance has anything related to the temperature? Means is it indirectly measuring the temperature, or it is actually measuring the observance?
Yeah, okay, what we finally have is the concentration. When we look at Lambert-Beer's law,
Okay.
of course the concentration depends then also on the temperature we have. But so we know this here. So this is so we have a known amount of these T3H3 iodide molecules, and so we know then of course the concentration at the beginning quite good.
Okay. My next question is, so we know the lot of negative things about the soot. What are the disadvantages of the soot? So how to focus on the advantages of soot? So because we cannot completely eliminate soot, so how to use that soot as for the benefit or in a positive way?
When you consider it with the combustion process,
Yes.
there is no positive way.
Okay.
So you should get rid of it. So
Okay.
and so in Europe the regulations are so high at the moment that the air at the end of a combustion engine, at the exhaust gas of a combustion engine, is cleaner than the intake air.
Okay.
And so, and considering the soot, for example, or particulate matters, here we have to use proper filters. And in these filters we collect these molecules and then they are reburnt finally. So there is no positive aspect with combustion. Of course we use, as I've shown you at the beginning, soot in a lot of different industrial processes, but we should avoid to spread soot in the atmosphere if not necessary.
Okay. Thank you.
So, what I observed is like benzene is the major precursor for soot formation, benzene. So, is there any way that we can avoid formation of that reaction? The way like we are capturing it at the end by using catalytic converters.
Okay, here I have to say I'm not the expert, so it may be possible, but the applications I know mainly try to get rid then of the soot we have formed. As I've said, when you consider diffusion flame, especially in a diesel engine, it's very complex. In the molecular zone to stop the formation of benzene. So for premix flames it's quite simple. You have to stay on the lean side or below a critical equivalence ratio. So if you are not too rich, then you do not follow this benzene formation pathway. But for diffusion flames, I'm not aware that it's quite simple to stop the formation of benzene at the molecular level already.
One more question, like if you have oxygen content, more oxygen content like we have seen in case of methanol and ethanol, can it be controlled benzene formation if I am adding oxygen in by some way?
So this we'll discuss after the lunch break. Yeah,
Okay.
so maybe we can discuss this question after the next lecture. It's okay for you.
Okay, okay,
Yeah.
thank you.
So no further questions? Okay, then enjoy your lunch. Thank you.
It's so much of chemistry.
Yeah, I was really surprised. I tried to go not too much into the details. So I hope that you have understand that we finally end at benzene, then form larger polycyclic aromatic hydrogens, and finally we yield soot. And I think this is enough. No, you don't have to know all the details. Okay. PAH, and finally we reached the Zoot zone where where larger molecules are formed. And there was a question in the morning: do we have a way to avoid soot formation looking on the chemistry? And I have answered it in a way that for diffusion flames, and this we have in diesel engines, this is difficult to handle. However, we will see now a possible way to avoid soot formation, and this is one of the concepts using a different new renewable fuels like the one we see on this slide here. So in classical diesel, fuel consists of maybe 100 of different species. So normal paraffin, isoparaffin, first simple cyclic structures, aromatic structures. We have to consider that we have a lot of different reaction pathways here. For biodiesel, there's one example here. There's the advantage, we have only 5 components here, mainly fatty methyl esters like methyl palmitate. So we see here a long aliphatic chain, and then here the ester group. So this of course looks much easier to handle, 5 compared to several hundred species. That's the first part. And the second part is we have here this carboxy group. So we have ester structures here where one carbon atom is already attached to 2 carbon dioxides. So here in this fatty methyl esters, you see it here, that too. So of course this helps, and I later will explain how it helps, but of course it has a disadvantage. We don't have carbon monoxide as an intermediate product. We directly may end at carbon dioxide. So this has to be discussed. So here you can see this methyl butanoate biodiesel, and here we have normally the first breakup of our molecule. That means ambiguous finally either CH3 plus CO2, or what we normally will prefer, CH3O plus CO, carbon monoxide. So we have 2 different competing reactions, and of course the question is, what is the preferred pathway here for this process? So here for this molecule DMC, we also have this ester structure, and so evidence theory experiments have shown that this first reaction is the preferred reaction, so that we yield directly carbon dioxide and not carbon monoxide, which then we can oxidize in our exhaust gas later on. So, and here we see again our reaction coordinate and energy. So we start here with CH3O plus carbon monoxide, and you see here CH3 plus carbon dioxide has much lower energy, so this is the preferred pathway here, so the final product. So when we consider again soot, when we look at classical explosives, trinitrotoluol or the TATB here. We have aromatic rings and a lot of CC bonds. But when we, the question is, do we get soot here? And one specific example, of course, here is RDX, also an explosive. So this does not produce soot. We don't have any CC bonds here. We have CN bonds. So there is no way to form soot in such a molecule. So oxygen is the main obstacle for soot production. So the idea is to have combustibles with carbon monoxide bonds, carbon oxygen bonds, sorry. There are of course many possible sources of oxygen. Simple alternative is air, to incorporate oxygen from air, but the more preferred way is oxygenated hydrocarbons, like the methyl esters we have seen. However, this is used anyway in a diesel engine to reduce soot production. Okay, this with the explosives I skip. So the molecular structure of the oxygenated fuel additive determines its soot reduction properties. So variability in soot precursor production observed computationally. Before modeling was used, all oxygenates were believed to be equally effective in soot reduction, but of course this is not the fact. Then engine experiments consist with model results, and we find out that this early CO2 production wastes available oxygen atoms in the process. So the analysis quite now was based on a single component diesel fuel surrogate. What we need in the future is more a multi-component approach. So as we've seen, so one specific additive may not fulfill the requirements. So even though we have discussed all the details today, when we look here at the numbers, it's still surprising. Why is it such a big problem? So soot is or carbon-based molecule, so it burns, of course. So the yellow flame we see is burning soot. So 99% of the soot formed in the engine burns out. So why we have not 100% combustion? So these soot particles burn, the yellow color. So we have a local temperature drop, and we may have some local extinction in the combustion engine, and these sooner burn kinetics are relatively slow, so require high amount of OH radicals, and that means more or less high temperatures, which is not always the case, and of course there is still a lot unknown about soot burnout. So what can we do? So I think you came later, so you have asked me in the morning, can we influence soot formation with respect or looking on the reaction mechanism? And I said it's difficult for a diffusion flame. But of course when we use additives like the oxygenated molecules we have seen here, so of course we can use the diesel engine as a diesel engine, but with proper fuel mixture maybe have a chance, or with a better process. So this is a classical plot, equivalence ratio versus temperatures. So we have seen high temperatures, especially high temperatures are leading to NOx formation. Especially thermal NOx is then we cannot no longer avoid, so our radicals attack the nitrogen molecule, and finally we yield at high temperatures a lot of NOx. And here if we use rich mixtures, which we have in diesel engines, where we inject our liquid fuel, which then breaks up, vaporizes, atomizes, and mixes with our air. So we have a broad region, but we also have, of course, some regions which are really rich, and there we have a lot of soot formation. So the question is, how can we use this knowledge to optimize the process? So first of all, this is the adiabatic flame temperature as a function of equivalence ratios. So at near 1 we have the maximum temperature. Rich and lean we have lower temperatures. So looking at this, okay, to avoid NOx we should be here, of course, in this area. But we should not be below around 1500 Kelvin, because then our CO to CO2 conversion gets too slow, will no longer contribute to our reaction process very much. So classical spark ignition energy, spark ignition combustion is in this area. The manufacturers always say we can produce lean combustion engines. So there was a lot of research to have their combustion engines here, but this has not happened so much. So most of the spark ignition engines are still here at phi equal 1. So we have a controlled heat release, we have controlled combustion timing, we have a wide load range. For NOx we can use a proper catalyst, but of course compared to diesel we have low efficiency too. So our diesel engine is somewhere here. So we have controlled heat release, controlled combustion timing, wide load range, high efficiency, especially the new diesel engines we have in nowadays. But of course again we have NOx, and here also particulate matter, so soot formation. And the idea is to reach this high efficiency clean combustion region. So what can we do to perform our process under these conditions? So it should be, of course, highly efficient, low NOx and PM emissions. But then the question is, okay, load range, combustion timing, transient control, and which fuel we can use here. There are several concepts like the homogeneous charge compression ignition. This is in this area here. And there is this dilute controlled diesel combustion. So where we have only an amount of 10% of oxygen, so highly exhaust gas recirculation. So we lower the flame temperature. So we try to be in this area. And then now we want to further discuss the practicability of these techniques here. So HCCI is premixed combustion. We are below equal to phi equal 1, and we have a volumetric reaction in the whole chamber, hopefully. So kinetics, temperature, mixture fields control the combustion process. Mixture preparation is very important And the limitations are difficult to control the combustion timing. We have to take care of NOx problems and eventually high NOx and also PM at high loads. This is one of the things with this fuel stratified ignition or HGCI engines. We suddenly have gasoline engines with soot formation, which has to be considered, of course. And we can have misfire, so incomplete combustion at light loads. So it's more difficult to control. The other concept, the dilute clean diesel combustion, because it's non-premixed, we are normally in the rich region, and we use traditional diesel plus a high exhaust gas recirculation. And now the idea is to add, for example, low sooting fuel or enhanced mixing. So the limitations here, so we need a high exhaust gas recirculation, and we may hit a smoke limit with EGR before attaining required NOx emissions. So it's difficult to handle then both limitations here. So we tried here to optimize the combustion process itself, but as it's difficult, so you need additional measures. So you need something like filters, for example. Another possibility is the so-called continuously regenerating soot trap. So the classical catalyst in a diesel engine is used to oxygenate carbon monoxide, and of course these higher hydrocarbons should also be oxidized. So this is a classical concept of a diesel oxidation catalyst. And there is a new concept where we use NO, which then is oxidized to NO2, nitrogen dioxide, and this reacts then with soot to form CO2 and NO again. And the idea is here then to reach below 50 ppm of soot and below our ratio of NOx to PM around 20. So this leads us to our NOx molecule. So NOx is of course one of the biggest problem dealing with combustion processes. So we have seen in the morning this smog over Los Angeles. So the NO2, nitrogen dioxide, is reacting with sunlight and then producing oxygen radicals. This can directly react with oxygen and air, forming ozone, which is not good for your health, but it also can react with other molecules, which then of course has a big influence on health, with the health issues. So there is of course limitation of a NOx. So, and this is strictly controlled nowadays in Europe. So There are, for example, zones when a specific level is reached, diesel engines no longer allowed to enter, and especially older diesel engines are forbidden in a lot of cities in our days, so that these cities can reach the limiting NOx concentrations. But before talking about this, we can maybe talk how do we yield NOx during our combustion process. So we have discussed in detail already the thermal NOx formation at high temperatures, so O plus N2 gives NO plus N. Then we have this prompt NO formation with hydrocarbons, so CH plus N2 gives HCN plus N. And there's maybe nitrogen bound to our molecules, which then also generates HCN. And finally, we have this nitrous oxide laughing gas mechanism, so N2 plus O gives N2O, and this reacts with a further oxygen atom to NO plus NO. And to get rid of NOx, we have to consider, of course, all four reactions here. So this we have discussed already in detail. So the thermal NOx formation, and with the assumption that the change of the N concentration with time is equal 0, because the formation and consumption has equal rates, we can calculate the amount of the change of NO as a function of time. And here you see the amount of O atoms is of course crucial, and again, if we have higher temperature, this concentration is increasing, therefore increasing here the reaction rate leading to nitric oxide. Prompt NO is a little bit more complex. So here we see the classical pathway starting from HCN to NO. But we can see that our CH radicals formed in the flame attack our nitrogen, giving HCN plus N. And there are possible other reaction pathways which may be considered. So CH2 plus N2 is may forming HCN, or it is giving H2CN, and this C radical may also attack N2, giving CN plus N. So the question is then, okay, what is now really happening in our flame? What is the important reaction here? First of all, okay, where do we get this CH from? This we have discussed last week already. So when we look here, for example, the classical CH combustion, the lean combustion is following this way. If we have rich combustion, we get some CH here, which then either is oxidized to CO, or of course can attack our nitrogen. And you see there are a lot of source reactions here leading to CH, and there are a lot of reactions leading to CH2. So this has to be considered. The interesting part here is So when we talk about this simple equation, CH plus N2, it is a spin forbidden reaction. I will not go here into the details, but when we follow here the energy potentials and the reaction coordinate, normally this transition here from this status to this status is forbidden. So of course it can happen, but normally not with the rates we assume. So nevertheless, there were a lot of experiments giving us quite high reaction rates here, which can be found in the literature. So this was astonishing. As I said, it's a spin forbidden reaction. So it should not be so prominent. And so of course further research was necessary. And the breakthrough came years later. They developed a new prompt NO mechanism, and this is mainly first based on quantum modeling of possible reaction pathways. And then, okay, it's quite fast here. Of course, they used proper experiments to support this assumption. So in nowadays we know much more about this pathway. So we do not form the other way around. So this reaction is strongly pressure dependent. It can be used to describe the reaction of Cn plus N. So you see how complex this mechanism looks, and so these molecules here, NCN and HNCN here, then can be oxidized to produce NO. So it is not going the assumed way we have seen with a spin forbidden plot, but it is involving a lot of equations here, finally leading to NO. So what happens to NCN? So NCN is formed by this reaction CS plus N2, and then it is one important pathway is here the formation of nitric oxide, but also other reactions can occur. And so the maximum NO reaction rate comes either from this pathway, so NCN plus O2 gives NO plus NCO, or we have this more or less classical way, N plus OH gives NO plus H. So it was possible to examine the process in detail, mainly based on quantum modeling. So then we have this reaction C plus N2. Why is this not proper reaction rate? So it just this Cn, which is formed from this reaction, is reacting further with an N atom to N2. So, or the reverse reaction of this reaction here is fast at room temperature and at tube condition. So we cannot assume that this reaction is an important reaction. So when we look now at our NO formation, for example, as of an equivalence ratio. We see that for rich mixtures, this is here, so we have lambda here and not phi. So 1 over lambda is equal 1 over phi. So from rich mixtures, we see a lot of prompt NO and thermal NO. Thermal NO, of course, is mainly near the stoichiometric mixture, and we also see some limitation for lean mixtures here, thermal and prompt and NO. So the question is, how can we adjust our combustion process to reduce both thermal and prompt NO? Of course, the ideal way would to be as lean as possible. So low flame temperature and low prompt NO formation. But as I said, with classical spark ignition engines, this has not been realized in mass production yet. Then there is this N2O road to form NOx, so nitrous oxide. It's more important lean combustion in low temperatures. So this is what I said. We would like to be here to get rid of these two formations. Suddenly we get a third reaction, which is important in lean combustion, where we have less prompt NO, and at low temperatures where we have less thermal NO. So for example, in stationary gas turbines, this has to be considered. Then this we will have maybe on Wednesday more in detail. Ammonia. So ammonia is here used as an additive. But of course, when we look at the oxidation of ammonia in flames, so ammonia is also forming NO. So here, and of course we want to reach N2 as a product plus water, but of course NO is also formed, but for ammonia flames this we will consider on Wednesday. Before I continue with ammonia, one possibility is this fuel stage burner concept. So we have an more or less rich flame here in this center where NO is formed, so where the temperature is quite high and so on. And then we have a so-called secondary reburn zone. So where we add air here and combustible eventually to form a tertiary combustion zone, and the idea is to reduce or reburn NO to N2. So this is a classical concept, especially for large power plants, coal power plants, for example. But the typical concepts we have are to get rid of NOx after the combustion process. So SCR, thermal denox, and rep-renox are the classical examples here. So selective catalytic reduction, SCR. We use a reducing agent. This is urea here. So in Europe it's more or less mandatory if you have a diesel engine also to have urea to reduce your NOx output. And this urea here, H2, 2 times CO, decomposes to ammonia plus carbon dioxide in using water. And then this ammonia reacts with nitric oxide, leading to N2 and water, and excess ammonia then is oxidized in our oxidation catalyst to N2 and H2O. So we start with urea and nitric oxide, and we end with N2 and water. So perfect process. Question is, why do we have it so complex? So here you can see it in a motor. So we have our diesel engine. Then first we need a diesel particulate filter to get rid of our soot. And then we have to add urea from this fluid tank. And then we have to use this catalyst to oxidize or reduce our NO towards N2. So why do we do it not directly on a catalyst? So NO plus or NO2 on a catalyst surface, leading to N atoms, oxygen atoms, and finally leading to N2 and O2. This concept exists, but we don't have a catalyst system which can do this directly. So we, at the moment, we always need something like urea for this process. One concept is also thermal denox. So we add again something like ammonia, and in a specific temperature window we produce mainly this NNH, which then with NO forms N2. If we do it properly, we end here. Of course, we can also go this way here, leading to NO from ammonia. So the temperature window is quite small, but in this temperature window we have 90% conversion efficiency. Then there's this RAPRI-NOx concept, so rapid reduction of NOx. So we have these isocyanic acid here, and I forgot the name of this molecule. So this is also a stable molecule. This is the simplest molecule consisting of the 4 important atoms of organic chemistry. So H, N, C, and O. It was more or less discovered 1830 from Justus von Liebig and Friedrich Wöhler. And Friedrich Wöhler was the scientist who was able to form urea from inorganic substances. So it was the first time that organic substances were produced by this way. Until that time, there was the belief that in organic substances, something like a vital thing. And so here shown, we are really focused here on chemistry. So this isocyanic acid decomposes to NH plus CO. NH then reacts with our NO, giving nitrous oxide. Or the main concept is maybe visible here. So we have this isocyanic acid reacting with NH2 or leading to NH2, and then this NH2 gives NNH plus NO. Again, this lead to so this way then leads to finally to N2. So, of course, when we know about these possibilities, we have to consider with the injection of urea that in reality both pathways occurs. So we have, when we look at this molecule, we form NH3 and we form either cyanic acid. So NH3 is used for this thermal denox path to reduce nitric oxide, and isocyanic acid is then used for this rapid NOx pathway. So we need, at least today, something like urea or we have to add ammonia, urea, species like this to reduce the amount of NOx formation. But these are classical engine concepts in nowadays. But in the future, maybe we can use other engine concepts like DC-DC or HCCI to reduce the formation of NOx and PM directly in the combustion process, which then of course would be cheaper because we get rid of all the exhaust gas treatment we have in nowadays. So I'm at the end and I'm open for questions. Thank you.
Okay, in one plot you have shown the cleaner combustion zones. So kindly can you go to that plot?
You mean this one?
Yes. So here, as per the plot, this SI engines are having a higher NOx side than the CI engines.
Yeah.
But in realistic conditions, this diesel engines are getting bans nowadays because they are getting the pollution content is more. So how to justify this one with this plot?
So what you mean with pollution content is small? Can you please repeat the question?
Yeah, actually in India, so nowadays this diesel vehicles are getting banned.
Diesel is banned?
Yeah.
Mm-hmm.
So over petrol vehicles means SI engines are more preferred over CI engines in terms of vehicles.
Mm-hmm.
So if these SI engines are producing more NOx, then why they are preferred more than the CI engines?
So both engines produce NOx.
Yes.
Yes. With gasoline engines, you can use simple catalysts. So, and with diesel engines, we actually have to use this urea concept. So, if you have a proper diesel engine, at the end you have clean air too, depending on your threshold. I know, why is it banned? Is it too expensive to use cheap diesel engines, or what you mean with banned?
Yeah, so I don't know exactly, is it due to soot or due to NOx? Because in Delhi particularly, if you'll see, so there is a huge ban on the diesel vehicles.
It's because of soot and particulate matter.
Yeah, so we have, in Europe we have several levels. So EU regulation 4, EU regulation 5, 6 and 7 I think is coming now, and with each regulation the allowed amount of soot and NOx leaving the end pipe was reduced. So, and as I've said, in winter time or now in most cities there is a forbidden zone for older diesel engines. I'm not allowed to enter this area anymore. I have to have a newer one. So maybe you have, so you don't have this concept here in India.
We do. It's
Yeah.
called
Bharat.
regulations.
BS6.
Bharat stage.
Currently on BS6, which is equivalent to Euro 6.
Yeah, but this is not banned then. So you have not banned diesel engines. You
Completely banned.
But there are huge restrictions on the use.
Hmm?
There are huge restrictions on the usage of diesel engines.
Why is the resistance there? Or from which side?
Yeah, maybe due to soot. It's particularly in Delhi side.
Mm-hmm.
Yeah, maybe due to soot and the particulate matters. So maybe not due to NOx.
Yeah, but again, if you use a proper diesel particle filter, you can handle this. But of course, it depends on the regulation you have. So what is your threshold you allow here? How much soot is allowed, and of course then what size of soot particles is allowed. So this, for example, has also reduced in Europe. So I think now we are talking about 23 nanometers particle size. In the future we will measure 10 nanometer particles, and also 1 nanometer particle size is at the horizon. And then of course you will face a lot of problems with your diesel engine. So you say they are banned, or they are not in use due to this.
Since they don't meet regulations, they aren't allowed specifically in Delhi area.
Mhm. So also quite modern combustion or diesel engines. So Euro 6, following Euro 6 regulation, or
almost it's very similar to Euro 6,
Mhm.
the BS6 regulations, but infrastructure, automotive infrastructure in India is not as developed as Europe or other countries. So we don't have as developed engines as developed diesel engines as Europe has. And again, use of SCR and such technologies is very expensive. So that hasn't come to India yet because of those reasons. So I think that is transforming slowly and gradually.
Mhm.
With time, I guess we would be seeing diesel engines with very less emissions.
Yeah, so this, what I want to say is, it's of course technically possible to have a clean diesel engine, no? And it's a very reliable and very efficient engine. So I'm driving privately also in diesel. It's a perfect car, but of course it's then a question of money. So especially with diesel engines, you may have to take further more actions compared to spark ignition engines.
Government is now mostly supporting for electric vehicles and CNG vehicles.
Mm-hmm.
So, as a cleaner fuel.
So you really have battery electrical vehicles in a larger amount here in India.
It's growing.
It's growing, yeah.
It's growing.
Mm-hmm.
Almost in all city buses, so they have been completely replaced
Yeah.
with the electric vehicles.
So in Europe, these cars are even more expensive than classical combustion engine cars.
Yeah. They are expensive, but due to this fuel,
Mm-hmm.
this cleaner fuel concept, so they are utilizing either CNG or electric.
Is there something in discussion like forbidden areas for combustion engines? So I just say here in this part of Delhi only battery electrical vehicles are allowed.
As of now, not like that, but only the diesel vehicles with high emissions are not allowed.
Mm-hmm.
The ones who don't at least even match BS4 levels. BS4 is similar to Euro 4. So those are banned, completely banned. They cannot even enter.
Yeah, yeah.
In majority of developed Indian cities, BS4 is the minimum regulation, but uh, so we are seeing more growth in electric vehicles.
Mhm.
So he explained that government is making infrastructure for the electric vehicles, electric buses especially, so that they are replaced. They replace the modern. They replace the older diesel buses. That basically, I'm trying to say that Delhi has very high amount of pollution, and they are trying to remove as much pollution as they can. So they have only electric vehicles there. I'm talking about government vehicles.
Mhm.
They are all electric, but private industries and buses that carry a lot of weight, they still use diesel.
Mhm.
So that is yet to be changed. They are yet to be changed, and EV infrastructure is growing. So even government is subsidizing private companies like Bharat Benz to go for EV vehicles over diesel vehicles. So we are seeing more of that.
How much diesel cars you have here in a percentage?
Diesel cars we don't have much in India. Most of the cars are SI engine only.
Yeah. But
But all of the trucks,
heavy duty engines,
heavy
yeah,
vehicle are diesel. But they
Yeah,
are
but-
replaced.
is there a ban there? So there's a replacement of the city buses maybe?
Yeah, city buses.
But what do you do with the trucks?
Yeah, trucks are government is subsidizing private industries to invest more in EVs rather than engines. So most of the companies are trying to develop their own EV infrastructure for heavy load duty,
Mhm.
heavy duty trucks.
So from Europe there's a clear plan to, I think there is a ban 2035 or so for combustion engines. Do you have a similar concept here in India?
Yes.
Yes? So what is your number?
2030.
Hmm?
2030 is the plan,
Mm-hmm.
but I personally think it would be till 2035 or something.
Yeah, of course. So we have to adjust the numbers.
Yeah.
Okay. Thank you.
As per many research, so are the EV buses are really pollution free? Because to prepare that lithium-ion battery, the amount of pollution that creates, so it is sometimes taken that it's equivalent of producing 6 or 7 diesel vehicles.
Yeah, but I've discussed it today with Professor Sahoo already. So the burning of the crop from the farmers, for example, this is forbidden now in Europe for 30, 40 years. This is also a possible way to reduce pollution. But I think this is not acceptable here or proper way at that time in India. But do we have further questions to the slides we have seen today? Okay, then maybe we will have some time for discussion afterwards. So we can stop this lecture now. Thank you.
KIT Kalinga Institute of Industrial Technology, Bhubaneswar. This is my PhD work where we have optimized the operating parameters of a biogas fueled engine. Now I'm just there is a little bit of background here where we have started, why we have started, and what motivated us. So as you know, most of the energy we are using is derived from the fossil fuel, and petroleum based fossil fuels are used mainly for transportation, power generation, and agricultural activities here around the world. And if you look at that BP Statistical Review World Energy 2019, we can identify that transportation sector is the major consumer for the petroleum based fossil fuels. And petroleum fuels, there are some issues with petroleum fuels like depleting reserves of the fossil fuel, intensified energy demand which rises day by day, and rise in the price of petroleum fuel, and of course the pollution part also plays a major role. But then what are the solutions we have, like alternative fuels, renewable fuels from non-fossil carbon resources, exploration of performance improvement methods in those energy conservation and transformation devices, exploration of emission reduction techniques. So these are some of the solutions through which we can address these issues that we have currently. Among the renewable fuels, we have mostly two categories, liquid and gaseous fuel. And mostly gaseous fuels are being considered advantageous over the liquid fuels because of few of the reasons attached to combustion. They had a wide range of flammability limit, and they can form homogeneous mixture, and even we can burn very lean mixture, and the hydrogen to carbon ratio is very high in those gaseous fuels. But we know the issues associated with hydrogen storage and transportation are the major issues. So biogas can, for at this instant, it can be for this era we can say that biogas can be considered as a attractive renewable source of energy for mostly developing countries, which consist mostly of CH4 and CO2. We have almost 60% of CH4 and 40% of CO2, along with some other impurities like hydrogen sulfide and nitrogen also. And what are the advantages here with biogas? The advantages, if you look at its physiochemical properties, the advantage is with its auto ignition temperature and research octane number, which is around 110 and 650. RON is around 110 and auto ignition temperature is around 650. So these are two major advantages that is qualifying biogas as a fuel, suitable fuel for SI engine. And most effectively, the combustion of such fuel do not affect the net CO2 in the environment, because it already contains CO2. Once we are going to complete the combustion process, the net CO2 emission is comparatively less than other fuels. So for this kind of fuels we need an energy conversion device. So what I need, like identification of a suitable energy conversion device for biogas to power generation. Mostly we are talking about an IC engine which can efficiently convert the available energy of biogas into work. And currently the available technologies are limited to limited and suitable for LPG and natural gases, and they are limited to high power multi-cylinder engines, and mostly those dual fuel engines are using the engines which are using biogas. They are mostly dual fuel engines that are using in pilot fuel up to 30 to 40%, and yield in high price of biogas fuel engines. Those are manufactured by Cummins, Prakash gas generators. So these are two companies which are manufacturing this kind of engines. Now significant use of there are significant use of low and medium low power single cylinder engines, medium to low power single cylinder engines in the rural and remote areas of developing countries, in the field of agricultural and decentralized power production. So, if you are going to devise something which will support this part, and the cost will be reasonable, though, so in that case we can consider that as it is a good innovation. Now, there are some issues with biogas, issues like it cannot be used alone in CI engine, because we have seen the auto ignition temperature is 650 degree centigrade. So, that cannot be the combustion cannot be initiated when we are using in CI engine directly as a standalone fuel, but it can be used along with the pilot fuels, either it may be liquid or gaseous pilot fuel. It can be used in both CI and SI engine. For gaseous fuel, it is essential to use SI mode because it is an octane fuel. So, it should be used in SI engine rather using in CI engine. It can be used in CI modified SI engines. So, we can also modify a CI engine and convert it into SI engine, and we can also use biogas with that engine, which can operate at higher completion ratio. But we need some major modifications when we are using when you are converting a CI engine for biogas application, like we need to detach the fuel injection system, incorporate suitable spark ignition system, modification of the engine intake system for air fuel mixing, reduction of CR to an optimum level, developing and governing system to support correct air fuel ratio. So, these are the major modifications that has to be done when you are converting an existing CI engine for biogas application. First, as a standalone biogas, when we are considering biogas as a standalone fuel, but rather when you are going to use an SI engine, we do not have to take much we do not have to handle much issues, because what we need to do only here, we need to change the engine the fuel intake system only. We need to have some modification in the engine intake system. That means the carburetor, conventional carburetor, has to be replaced by a gas mixer, and that gas mixer need to be designed properly. Again, with as in the beginning I told you, there are some performance improvement methods which can also positively influence the devising of this kind of engines, like the techniques like variable compression ratio, fuel enrichment method, optimum ignition timing or spark timing, and pollution control methods like excess air supply, exhaust gas recirculation, and catalytic converters. So, with this kind of involvement of this kind of technology which is being listed out here, we can also improve the performance of this kind of engines. Now, the objective here where I had done my PhD work, the objective was to devise a low cost 100% biogas fueled SI engine. So, since it is not biogas engines are existing, as I told you, but the price is too high and the power output, it is not applicable to medium and low power single cylinder engines. So, the objective here is to devise a low power medium to low power output range single cylinder engine which can applicable to decentralized power production or in agricultural applications. Now, what we have done, we have started analyzing an engine, commercial available engine in the beginning. So, we have persuasion commercial available engine, which is a constant speed CI engine, which is converted into SI mode. So, firstly we have done an experimental investigation of a biogas fueled customized commercial SI engine, which is commercially available. We have customized this to vary its compression ratio. Then what you have done, we have played with its operating characteristics like compression ratio, brake load, and then we have identified the parameters and we have studied the issues, what are the issues with those kind of engine, and then we have identified issues like derating of engine power, inefficient governing system, and then based on that we went further and we work on a second engine, which is a research engine setup where we can use different kind of fuels. It can become that is what is called a variable compression ratio research engine setup. So, in that engine we can play with the compression ratio, we can play with the ignition timing, we can use fuels like diesel, we can use fuels like petrol, hydrogen, methane, everything we can use it there. But some modifications we have to do in order to accommodate those fuels. So what we have done, we have used this engine, the VCR, the second engine, which is a VCR SI engine, and then we have done some baseline study with gasoline, because this engine is mostly designed, and the characteristics of those engines are mostly designed for gasoline only, but we can use different fuels in this engine. And to record to have a reference line, we have first operated this engine with gasoline, then we have done a baseline study with methane, then we also done with a baseline study with biogas. At a fixed compression ratio, we have used 3 different fuel and we have compared it. Then what we have done, after the comparison, we found out that what is the issue with this engine when you are operating with biogas. So like we know that methane, when you are talking about methane, it is pure methane, 100% methane, but biogas contains 60% of methane. So there will be obviously derating of engine power. Gasoline also, it is the power output of those engine when you are using gasoline is obviously high. But in order to accommodate these losses, can you do something? Can we do something? So for that we have identified the issues, issues associated with the VCR engine when you are operating with biogas. And at the third stage, we have purchased a normal SI engine, like Honda GX200 engine, which are mostly used for land movers. And then we have in this engine, the issues what we have identified in the second engine, which is a VCR SI research engine setup. We have done some kind of analysis here. We have played with the operating parameters. We have identified the optimum operating parameter in the VCR SI engine, and we have implemented those parameters in the third engine, which is a pure SI engine, is pure commercial SI engine, which is applicable for land movers or some other kind of application. It is a Honda made engine. And so the operating parameters what we have optimized in this engine, we have implemented here, like we have found out an optimum operating compression ratio for the biogas when it is operating in CR, when it is operating with the VCR engine. We have identified the ignition timing, we have identified the optimum air fuel ratio, we have identified the throttle position, and then we have fixed all those parameters in this engine, and then we have studied the third engine again. So 3 different engines are there, but what is the common between these 3 engines? The rated power output of all these 3 engines are constant. So the first engine is designed to produce and brake power of 4.4 kilowatt. The second engine is designed to produce and brake power of 4.4 kilowatt, but the third engine is somehow designed to produce and operating the power output of around 4.3 kilowatt. Okay. So then once we have implemented all those optimum parameters in the third engine, we have compared all these 3 engines with the maximum output condition. So that is what is the summary of my PhD work here. So I will take you step by step to each and everything. So this is what an commercial biogas engine, which is a normal, very normal engine, which is installed near a biogas plant. We have here in outside our IIT campus. We have designed a setup like also go further and show you what are the modifications we have done in this engine to for capturing all the parameters. And this is the VCR SI engine we have in our transit complex. This is the second engine and this is the third engine. This is both of these setups, engine 2 and engine 3 engine setups are in transit complex. Next is about the fuel properties, because we are dealing with 3 different kind of fuel. We are going to compare all these fuels, gasoline, methane and biogas here in this engine, because it is a VCR research engine setup. We are going to compare all the fuel here in order to get a baseline so that we can compare when we are designing it. Okay. So these are the properties of gasoline and methane biogas. If you look at some of these things like stoichiometric air fuel ratio, you can see it's 14.7, here it is 17.23, here it is 5.51. All these are calculated values.
And if you see the research octane number of methane is higher than that of biogas, and it's higher than that of gasoline also. Flame sheet, if you see the auto ignition temperature is around 650 degrees centigrade. Here it is 540 to 600, here it is 257, and flame speed is in biogas is very low, which is a very negative point about biogas. Some of these values we have calculated, some of have taken from the reference. Now the biogas what I am going to use, we have analyzed its composition throughout 2-3 years. We have taken the average of that, because the digester what we are using, the biogas produced from that digester changes with the ambient temperature, composition and other values. We had N2 and H2S. We cannot do anything with N2, but we can scrub out H2S moisture from this biogas when we are using it, because if you are not going to scrub H2S and moisture, it is going to damage your engine component. So we have also designed a few devices to clean H2S and moisture by taking only this indigenous materials, like for scrubbing H2S we have used annealed steel chips. We have packed in a column, pass the gas, pressurized gas in that column, and at the end we have compared the composition of the gas which is passing through that annealed chips column, steel chips that we are getting from turning and milling. So those steel chips are being used there to filter out H2S. Similarly, we have used blue silica gels to capture the moistures. So after refining it, so let us say this is the biogas digester, which is the site. It is a digester which is buried under the ground, and the cubic capacity of this digester sorry, each digester is of 3 meter cube. So we had series of digesters, like 4 digesters we had, around 12 meter cube. So it is producing 12 meter cube of gas per day. So we have used it, and this is that engine setup. The picture is not clear, but we will see the line diagram later on. We have attached an crank angle encoder here. This is exactly a biogas generator which is manufactured by Prakash. We have done some modification in the compression ratio. The rated compression ratio of this engine, when as defined by the manufacturer, is 13.94, but in order to see what is the effect of the compression ratio on all other parameters, we have done little modification at our end. And then this generator has to trap the in cylinder pressure and temperature and the crank angle. We have attached a crank angle encoder here, and then a pressure sensor here in the engine cylinder, inside the engine cylinder. And then for measuring the gas flow, we have a biogas flow meter. Airflow, we have a U2 manometer, and then we have a manual load bank, which is consisting of an wattmeter, load panel, and voltmeter and ammeter. From there we have calculated what is the electrical load, and then we have calculated the engine torque and efficiency. So it's again a water cooled engine. Now we see this is the block diagram, where now the most important thing is here that it's a constant speed engine, it's not a variable speed engine. So we had a governor here, and this governor is controlling the throttle valve basis on the load on the engine. What much the amount of, if you are going to increase the load on the engine, it's simultaneously what is happening, the governor which is attached to this flywheel is going to control this throttle valve, so that more amount of fuel can be entered to the engine. This is that biogas digester, 4 biogas digester, which is connected to a integrated biogas storage unit. Then it is attached to the moisture filter, and then H2S scrubber, and then it passes through the biogas flow meter to the engine. This is the air drum, and then it is connected here. Now what we have done, we have changed the compression ratio of the engine. As I have told you that the rated compression ratio of this engine was here 13.94. with some attachment of spacer plates and gaskets. We have continuously replaced it and done this kind of experiments there, where you have changed the compression ratio from 10.52 to 15.92, and this is the rated compression ratio of the engine. We cannot alter the ignition timing in that engine because it's a mechanical ignition, mechanical attachment, where we cannot adjust it accurately. So we left it, we do not disturb it, we kept it constant. With this constant ignition advance, by varying the compression ratio and by varying the electrical load, we have measured the brake power, VSFC, brake thermal efficiency, airflow ratio, volumetric efficiency. We have captured the P theta, and then from there we have calculated the mean gas temperature, net heat release rate, mass fraction burnt, and the emission components, CO2, SC, NOx, and CO. So these are some of the graphs which is here to find out what is the issue with this engine. Now, if you see, when you are operating this engine with all this compression ratio, the maximum brake power what you are getting is around 2.9 at CR 15.29, and the maximum brake load what it can take is up to 75%. We cannot go beyond that, 76% around. And at the rated CR, the blue line here, rated CR, again we cannot go beyond 70, we cannot go up even up to 75%, and the rated brake power is within 2.7 kilowatt. However, the rated brake power of the engine is around 4.4 kilowatt, but at the end what we are getting is different here. Now, if you see the engine speed, since it's a constant speed engine, which is meant to provide, which is designed to produce electricity, and that generator has to be rotate at a constant RPM, because if the RPM is going to fluctuate, the V and I coming out of that generator is going to fluctuate. So in that case it should remain constant, but it is not remaining constant here. If you can see, when you are going to increase the brake load up to 50% brake loading, there is a deviation of engine speed around 10%. So this is what is one more observation we have seen there. Now rest are thing fine, but if you see the maximum brake thermal efficiency, it's around only 18% when you are operating it at CR15. Volumetric efficiency is very low, it's around 28% only. Now these are some of the pressure data, in cylinder pressure data, where this is what is also supporting our what we have obtained in our performance analysis part. Now, if you see here, the data are a bit non-continuous here, because here only we can able to capture 10 cyclic data. In each cycle we are able to get 720 data point, and again 720 into 10, that is 720 data points only in between 0 to 720 degrees. So it's not much accurate in this case, but we do not have any kind of support in that time. So that's why we have got this data here. And if you see what is happening at this point, the peak cylinder pressure at 50% loading condition, the peak cylinder pressure is only about 14 bar here at around 50% brake load condition at CR10, sorry, this is CR10, and if it is CR15, the peak cylinder pressure goes up to 24 bar, and the peak cylinder pressure keeps on shifting towards the expansion stroke when you increase the brake load. Now, if you see the brake load here 76%, now when you are going to increase the brake load, the peak cylinder pressure is going to shift towards the expansion stroke. And of course, when I have only taken 50% brake load condition, because we have seen that up to 50% load only it is working fine. After that there is a deviation in the engine speed, that is why I have only placed this one. Now, if you see the mass burn fraction here, this is the time, like rapid burn angle. Rapid burn angle is the duration of duration in which the fuel starts, the combustion initiate, the combustion propagates and it ends up to 90%. The duration between 10% of mass burn fraction and 90% mass burn fraction is called rapid burn angle. So, if we can see here that rapid burn duration is going to reduce when you are increasing the compression ratio. Now, if you the CO emission, SC emission and the NOx emission is here, and if you see like the CO emission is reducing when you are going to increase the compression ratio, SC emission is also reducing at CR 15, and but there is NOx emission at higher compression ratio. Now, what is the final judgment in this observation? The operating engine operating at the rated CR, which is 13.994 and maximum brake load condition 74%, declined the rated speed of the engine by 9% and deteriorated the engine power by 34%. Then this is one of the major observation which need to be take care. Then the next one is the maximum achievable brake power, brake thermal efficiency of the commercial biogas engine that we have taken is only 2.88 kilowatt and 14.84% is its brake thermal efficiency. If you see the CO, SC and NOx emission at the rated CR, the CO emission is 0.11%, SC is 116 ppm and NOx emission is 151 ppm. So, these are the issues that we are going to address in our next step by using this variable compression ratio engine. But the issue is what? We do not know at what compression ratio we have to operate. We do not know at what ignition timing we have to operate the biofuel in this engine. We do not know what should be the air fuel ratio that has to be maintained in this engine. So, first of all we need to find out that, and then we can have a range and play with that. So, what we have done here? So, if you see the engine setup here, it is a 4.5 kilowatt, it is a engine single cylinder 4-stroke multiple SI engine, which is able to produce 4.5 kilowatt at 1800 rpm when operated with gasoline only. It is the rated engine capacity at gasoline, with gasoline. And we have the rated CR, it is a VCR engine, so we can vary the compression ratio, but when you are going to vary the compression ratio of this engine, the rated VR of the variable VCR range of this engine is 10 to 18, 10 to 17, but when you are using biogas we cannot, we have seen literatures, we cannot go beyond 14, 15. So, we need some lower range and higher range in between 14. So, again we have attached and we have modified the VCR mechanism there in the engine, and from there we are able to operate the engine in between 8 to 14. Now, in this case it is 16 to 10 for this experiment, and the next stage we have varied in between 8 and 14. As the cubic capacity is 661, and we are using like if you see there, we are using we have transporting biogas to the lab with the help of balloons. We are using a compressor here to compress it around 2 bar, and then we are able to supply here through a diaphragm pump attached to the engine. The diaphragm pump is operated with the help of if you see the diaphragm pump. So, it is an intake biogas induction mechanism where we have H2S scrubber, moisture trapper, and then a compressor, pressure regulator, fuel meter and a diaphragm pump. So, this diaphragm pump has 2 sections along with a inbuilt heater. There is a driver section and a driven section. Driver section is operated with the pressure drop in the engine intake manifold. When there is pressure drop, it attract or it pull the diaphragm towards the driver section, so that there will be pressure drop in the driven section, and by that what will happen, the biogas will flow from here to biogas mixture, and there is a heater here which is connected with the exhaust from the engine. So, the biogas will be again ultimately heated and supplied to this biogas mixture which is connected here. And similarly we have we have some measuring techniques. We have attached some instrumentation here, pressure sensors and crank angle encoders and throttle position sensors with this engine, so that we can recorded the required data. This is the VCR mechanism what we are talking about. So, we have formulated some formula to find out the gap that has to be maintained in between the piston top and the liner top. So, this is the gap which is like 1.8. So, this is the gap between the piston top and liner top. If the gap is maintained properly, we can able to achieve the compression ratio what is being listed here, and that can be maintained by using this lever which is available here. Similarly, now to operate the same setup with methane, we haven't done anything, just but attach on CS4 cylinder with that, so that it can operate with that. So, so now as I told you that we do not have any clue to operate at what compression ratio and or to operate at what ignition timing. So, in the base experiment what we have done here in this engine, we have found out what should be the compression ratio and what should be the ignition timing, so that this engine can be operated with biogas and methane. And then we have compared the same engine with gasoline, methane and biogas, so that we can find out a list of range of ignition timing we can play with further to optimize the engine for biogas application. So, here there are some basic results in that engine. So, I am just going to tell you what we have found out here only. So, here what we have found out, we have operated the engine with biogas at a compression ratio 10, and then we observed that at CR10 we are able to find out the optimum ignition timing at 40° crank angle before top dead center. So, because the maximum brake torque what you are observing here at 40° BTDC. Similarly, if you are going to vary the speed, also there is no much variations here, like 39, 40 and 41. So, 1° variation is there within the speed range of the engine, and from there we have understood that if I am going to operate the engine at CR10, the optimum ignition timing should be 40. Similarly, to support this, we have done the combustion analysis, where we can able to find out whether the area under the PV diagram what you have obtained and what you are claiming to be the best, because we are getting maximum brake torque there, here, and maximum brake power also here. So, it should also reflected in the combustion chart. So, we have calculated the area under the PV curve and we found out that the area under the PV curve, like IA40, if you see, it is highest 3264.94, the area under this curve is highest. So, we can say that this is the ignition timing with which we are getting maximum power. Now, similarly, for the biogas fueled engine, we have also got the optimum ignition timing, where we have seen that ignition time when you are operating at 40° crank angle BTDC, you are getting the maximum brake power and brake torque. That is also supported by the combustion analysis, where we are getting maximum brake area under the curve PV curve at ignition IA45. So, it is, if I am going to advance the ignition timing 45° before TDC, then it is giving me the best result, best brake torque and brake power. I am not going to the combustion here. Now, this is what is comparison of those three fuels in the same engine at CR10. So, if you see here, this is biogas, this is methane and this is gasoline. Now, if I am going to compare, obviously as we know that the engine operating with gasoline will have maximum brake power and brake torque, and followed by methane and biogas. The same thing has been observed here, but what is the thing that has to be noted here is the shift of pressure peak. When you are operating the engine with biogas, the pressure peak is shifted by 4° crank angle compared to the gasoline, and if you see the area under the curve also, the maximum brake power is maximum area under the curve at when you are operating the engine is with gasoline is highest, and followed by methane and biogas. Now, this is where from where we have understood that Now the engine, that the VCR research engine, can be operated with biogas, methane and gasoline, and we have some reference data at the base compression ratio. We found out what is the ignition timing with which the engine can now operate, what is the range of ignition timing with which the ignition time can the engine can operate. But as I told you that the auto ignition temperature of biogas is very high. It can operate at, the engine can be operated at higher compression ratios. So in order to find out the optimum compression ratio and its corresponding ignition timing and its corresponding equivalence ratio, again we have designed some of the experiments where we have changed the compression ratio, kept the throttle position constant, but if you have seen the previous slides, part throttle position is not going to affect much. So we are operating the engine at wide open throttle condition, keeping the spark time, we are varying the spark timing from 23 degree to 53 degree. This is the range through which we can upper and lower range we can say. If you are going beyond below 23, the engine is going to there is misfire, and if you are going to above 53, the engine is going to knock. So we are operating in this range, and then we are also varying the engine's speed, and then we are getting the parameters. Now to see here what we have done, we have varied the ignition timing and also varied the compression ratio. If you see one of the compression ratio, let us say this one CR12. Now if I am going to advance the ignition timing, the maximum brake torque is going to increase here. So the maximum brake torque that we found is around 24 Newton meter at 33 degree BTDC at CR12. Similarly, for each and every compression ratio, we have listed out what is the maximum brake torque timing and what is the maximum brake power output that can be produced at a particular compression ratio. So, but it has to be supported it has to be supported by the combustion and emission analysis. If it is not being supported by combustion emission analysis, it is not going to be worth. So if you see the brake thermal efficiency, as I told you, like this is the list where if I am going to operate the engine at CR8, my MBT timing should be 53. If I am going to operate it at 10, my MBT timing should be 45. If I am going to operate it at 12, corresponding it is 33. And if I am going to operate at 13 and 14, it should be like 29 and 25. But at what it has to be operated, that we have to find out. Now if you see the brake thermal efficiency, the brake thermal efficiency is maximum here at 33 degree BTDC at CR12. So this will give us an idea that even if you are going to increase the compression ratio with an equivalence ratio of, I haven't mentioned here, with an equivalence ratio of 0.79 to 0.8, low equivalence ratio, the engine is not going to produce much power or torque at higher compression ratio. So the limit is CR12 here. Similarly, if you see the BSFC, brake specific fuel consumption, is minimum here at CR12 when you are operating at 33 degree BTDC. Now these are some of the combustion analysis. I am not going to talk about it right now. Now this is what, if you see the same analysis, because we cannot blindly say that at 33 degree BTDC it is producing the maximum brake torque. It has to be supported by some combustion analysis. If you see this mass burn fraction and the PV diagram here. Now the area under the PV diagram we have calculated here at ignition advance of 33 degree crank angle at CR12 when you are operating at an equivalence ratio of 0.79 to 0.8. The area under the curve is maximum here, and it is around 2556, which is maximum among all the ignition area covered by the all ignition advance. Similarly, if I am going to the mass fraction burnt, the at angle 30 at an ignition advance of 33 degree crank angle VTDC, the rapid burn angle, the duration of burning between duration of crank angle in which the mass burn fraction is between 10 to 90% mass burn fraction is being achieved. That is being achieved within like 24 degree crank angle. So within and duration of 24 degree crank angle, the mass fraction burnt, the delta theta v, which is rapid burn angle, is being covered. Maximum amount of fuel is being burnt in that duration. So if you see rest of them, they are more than 24. It's 27, 26, 25, 25, 26, 27, 26. So from here also we can say that this is the point, this is the ignition timing that has to be maintained for this kind of engine. Some tables are there. Now if I am coming to the emission analysis, in that case to optimize the ignition timing. Now if you see at CR12, the black one, CR12, the CO emission, if you see the CO emission here, it's in the middle range, not higher, not lower. But one thing we can observe here, when you are going to increase the compression ratio, at CR12 we are getting maximum CO. The CO emission is maximum here in this case. So it will be reverse when it is CO2 emission. Now if you see the SC emission, the SC emission is minimum when you are operating at CR12, and when you are going to increase the compression ratio, the CO emission is highest at CR8, and it is minimum at CR12, and although like CR14 we are getting more than CR12. NOx emission, if you see, NOx emission is at this 33 degree crank angle BTDC, the NOx emission is higher here, CR12. This is because of the temperature effect, maybe. Now this is where we have seen at what compression ratio, what ignition timing we have to maintain. Similarly, the rest of the experiment are being done to optimize the compression ratio, at what compression ratio it has to be operated. So if you see here, like compression ratio, and this is MBT timing, and these are the speed. But because if you are going to vary the speed, the ignition timing also plays and is going to be changed. The optimum ignition timing will change. Since the range of ignition timing is very low here, like 1400 to 1700, the domain is very narrow here, it's not going to create much effect here. But in reality, if you are going to vary the speed, let's say 1700 to let's say 3000, then there will be a variation. But in this case, there is no variation. The maximum brake torque is again observed here at when you are going to vary the speed. The maximum brake torque is observed at 1400 RPMs, because in that condition the engine load is high, speed is low, engine we are going to apply maximum brake load there in that case. So the brake torque output and brake power output is high in that case, CR12, and brake thermal efficiency is high there. If you see, it's around like 32%, and if you see the brake specific fuel consumption, it is 0.65 kg per kilowatt hour. Now there are supported analysis for combustion, the PV curve, where the indicated power and brake power output is being calculated from the area under the curve. And if you see at CR12, now all this, if you see the ignition timing when you are operating this engine, like when you are operating the engine at CR8, the corresponding MBT has to be set up. So I have written the ignition timing is MBT for each and every compression ratio. The engine is operated at MBT, but in earlier study we have operated it at different ignition add-ons. Here it is fixed MBT. So when you are operating the engine at a fixed ignition timing, then we are able to trace the plot, PV plot here. So if you see the indicated power output here is 3.7 and this is 3.0. The rated output of the engine is 4.4. Earlier we are getting around 2.8. So this is what is the improvement here. That's all. And if you see the emission analysis at CR12, the CO emission will be very high at high speed condition. SC emission is low here in CR12. NOx is obviously high, it will be high because if you see the EGT, engine exhaust gas, the temperature is around 375 around 375 degree. Now all these are what are the work done in this second engine, what I told you is a VCR research engine. So what we have done only, we have got the third engine where I told you it's a commercial SI engine which is applicable for, which is mostly used for the lawn mowers. So we have converted that engine to operate with biogas. So as I told you that we need to design a biogas mixture. So what we have done some simulations. We have designed, we have done multiple settings, and there we found out what should be the tube diameter, because this are fixed, because this is connected to the engine inlet. So this end diameter is fixed, this end diameter is fixed. So we have to find out the diameter of this pipe in order and we have to look for that what is happening, whether the mixture is homogeneous or not when you are mixing it. This is the pressure profile when we are mixing it. This is the this is the pressure profile, sorry. This is the pressure profile where at the thought the pressure is dropping, and the velocity profile, if you see, the velocity is maximum there, and if you see the mass burn fraction after at around the exit of this biogas mixture is mostly homogeneous, not exactly, but somehow it is homogeneous. With that dimension, we have attached that biogas mixture here in this engine, and then we have tested it. And the optimum compression ratio, as you have seen, we have obtained CR12, but we are not able to implement it here because of limited design specifications. So we have done some kind of adjustment like technical adjustment where we are able to achieve only CR9. So with CR9 we obtained, we have measured the cylinder, we have measured the volume of the clearance volume, we have measured the clearance volume space, all those things we have measured, but we could not able to attain that compression ratio in this engine because of the manufacturing difficulties. And then there is we have done the performance analysis where we are able to operate the engine in between the speed and a compression ratio of CR 9.53, exactly CR 9.53, and the maximum brake torque output is 12 Newton meter, and the maximum brake power output of this engine is around 4 kilowatt, but the speeds are different here. And then if you see, I have an comparison diagram. As I told you, there will be comparison at the end. So what we have compared, I have taken 3 different engines. The engine 1 was a commercial biogas engine, the engine 2 was a VCR research engine, the engine 3 is that what we have implemented, the optimum parameter where we have implemented it. So in all these 3 cases, when we are operating the engine at biogas, it is producing some maximum power, maximum efficiency, maximum let us say emissions. Okay. So we are comparing that only for this 3 engine by taking this. So this if I am going to compare, this is engine 1, 2 and 3. So if I am going to compare the brake power output, the brake power output of the engine is around like this red one is brake power. So when you are operating with engine 1, the brake power was around 2.8 as I told you. Now when you are operating it with the VCRSI research engine, where we have optimized the parameters, after optimizing, this is the result where we got around 3.6 or 3.8, and now when you have implemented it in engine 3, the brake power is around like similar to the commercial biogas engine, but the compression ratio is low here. When you are operating, if you see, the engine 3 is operating at CR 9.5, MBT is 50 degree crank angle, but if you see this 2, the operating compression ratio is higher than this. Although the operating compression ratio is higher, we are able to match the same brake power with the third engine. The brake thermal efficiency, if you see, compared to the commercial biogas engine, what you have designed, the brake thermal efficiency is around 30%. Here it is around 18%. The maximum brake thermal efficiency we have obtained with the VCRSI engine is around 34%, but here we are able to achieve around 31 or 32%. Similarly, if you look at the CO and CO2 emission, the CO2 emission of the engine 1, the engine 2 is very minimum, where we have implemented the optimum ignition timing and compression ratio along with the equivalence ratio that has not been shown here in this presentation. But if you see here, the CO emission is around 0.2 ppm. This CO emission is around 0.2 ppm, CO2 emission is around 7%. This is the SC and NOx emission. If you see, the NOx emission is higher in engine 3 because it is operating at high speed, around 3300 rpm, I think, sorry, 2347 rpm. Because of that, the temperature is rising there, but in all these two cases, the operating compression speed is low, 1650 rpm. That's why NOx emission emission is higher. But if you see the SC emission, the hydrocarbon emission is low there. So finally, what you got, the brake, if you are comparing the brake power, brake thermal and brakes BSFC and the volumetric efficiency of the biogas fueled retrofitted Honda GXSI engine is improved by 2.25%, 51%, and the BT and brake BSFC is improved by 51%, brake power is improved by 2.2%, and the volumetric efficiency is improved by 32%, even if we are operating at compression ratio 10. And now if you are looking into the the emission part, engine 3 is produced lesser CO2 and SC emission with respect to engine 1. So this is what is the final output of all my sayings. There are some conclusions, technical conclusions here. Thank you.
Can you please show slide 38 again? So you said that on the last slide you have shown that the engine 2 has
this is engine 2.
Yeah,
This is slide for engine
2, and on your last slide you have shown the comparison of the NO emission, NOx emission.
It's 1500 around 1500 ppm at CR12.
Maybe your plot, I do not understand your plot. When you go to the last slide, so here we are around 1500.
This is for MBT, sir. This is for when we are finding out MBT.
Yeah.
This is 1500 ppm. But after that, we have again went for compression ratio. With that ignition timing, we have operated the engine at CR12 and equivalence ratio, which is optimized 0.7 to 0.8, phi is 0.7 to 0.8. And then if you see the NOx emission here, the NOx emission at CR12 is this one now.
Yeah, still 1500.
Still 1500.
Okay.
Yes.
So when you go now to your last slide, 57 or so. So this one. So engine 2, what is the NOx you have here? 300.
300.
So this I do not understand. So what is the difference?
I think it's being subtracted here. It's 1500 here. Let me see.
There's also 1500, I think so. For this.
It's around 300. Just this moment. No. Is like a mistake. Where it should be here only, I think.
Yeah, so I'm just wondering.
Yeah, so like 1500. It's.
You have said at the beginning, slide 8, that you want to capture all parameters. What do you understand with all parameters?
This one?
So you said you want to capture all parameters. So
Achha, parameters means like parameters. What I am capturing is engine cylinder pressure, crank angle data, inlet pressure, inlet charge pressure at the throttle body, and we are calculating like mass flow rate of the fuel, mass flow rate of the air, engine load. All these are we are capturing along with the emission data. All these are being captured by using an electronic control unit, and rest what I have shown you, like net heat to release rate, mass burn fraction, mean gas temperature, we are calculating it by the from the equations.
Okay. Can you show slide 11 and 11?
Yes.
So you said at 10 you have a valve which can control the inflow depending on the demand you have with the engine.
Yes, yes,
Yeah.
yes, yes.
Is there a storage system for this
The,
biogas, or what is happening? So if there is no demand,
Uh,
like you produce all the time with the biogas, what is happening then?
there is no demand. You're saying like there is there is no load on the engine.
Yeah.
the
So what
generator.
is happening with your output or production of biogas? Do you have a storage system there, or is it just an overpressure valve and you put it to the atmosphere?
There is no this any kind of system. So the system what we have built to analyze the system, like if there is no load, we can just, there is a manual valve, we can cut it down.
Yeah. Okay. So can you go to slide number 12?
Yes.
Maybe. Okay, we will continue with 14. So here you said you have averaged over 10 cycles.
Yes.
Is it right?
Yes.
So it still look not so smooth, is it?
Yes. We are normalizing it because the 10 we have only 10 cycle data, and the rest of the graphs what we have seen for p theta here, this is 100 cycle data.
Yeah. Okay.
That's why it is looking smooth.
Yeah.
And there only we are able to, because the system only we have built it, like that's why the instrument what we have used to only capture what minimum is possible.
Okay. So then can you go to slide 15? So on the right you have NOx,
Yes.
NOx formation. How have you measured the NOx?
NOx when it is here 13, this one.
No, so which method you have used to measure the concentration?
Achha. Like we have an GIAN 44 an analyzer. So it's for measuring NOx. I think it has a sensor which is an electrochemical sensor. And we have a device like for measuring emission. We have emission analyzer, 5 gas emission analyzer, which can able to measure H2, CO, CO2, SC and NOx.
And so is it necessary to calibrate this regularly?
Yes,
or-
yes, yes.
Yeah?
We have standard gases, we calibrate it.
Okay. And then finally, what is your measurement uncertainty?
It's there, but I haven't shown here. Measurement uncertainty, for emission it is different, for other like performance parameter it is different.
For NOx, for example.
It's like 1%, I think, around 1%, 1 to 2%.
Of the
Measured values.
okay.
Like we can see, like we can, if you are going to plot the standard deviation, it will be 1% up and down.
Okay, so these are my questions.
Okay, my question is on slide number 17.
17.
Because I face the same problem during while I'm doing my own biogas compression.
Here.
Yeah.
Huh.
What is the maximum pressure that you compress biogas?
Here. 2 bar.
2 bar. Okay. But in compression, during compression, in normal compression.
You see, we are maintaining around, I think, 3 to 4 bar. Once it is stored, we are controlling it here, this with a pressure regulator, which we are able to supply with 2 bar.
But is it sufficient amount of
Pressure drop.
No, biogas, is it available sufficient amount to compress the biogas?
You are talking about the amount of biogas.
Yeah,
Yes,
amount
yes,
of
yes,
biogas,
yes. We have a large balloons, which is capable of storing 2 cubic meter. So with one balloon we can do one experiment completely. Like you can change the pressure ignition timing. For all that it is sufficient.
Okay, another question is what is the maximum temperature? Ignition, on your table you showed maximum ignition temperature for biogas. It's around 600.
So it is depend upon the compression ratio what you are maintaining. If you see, this is so I'll show you.
I think it's
MGT. I see mean gas temperature. When you are operating at CR12, it goes around 1600 Kelvin here, and if you are varying the speed again, the maximum temperature here, I think this one here, MGT here. At what point you are looking, that is also important. At what angle? Maximum temperature here, when you are operating at let's say 1400 RPM, maximum temperature here it comes like 1100 Kelvin.
No, I understand, because if you are compressing your biogas at higher pressure, the temperature will rise. Because of that one I am asking, but at 2 pressure, at 2 bar, no problem. That's right.
Yes, yes.
Okay, thank you.
Thank you. It's not 1700 Kelvin, this is actually pressure plot, this is temperature plot, this is MGT, this is pressure. Okay. Thank you.
Tomorrow, I think there are 2 online presentations. Tomorrow there are 2 online presentations in the tutorial part. So students will present through online.
Okay, this will be the tutorial, yeah.
And this is a tutorial. That will planning to bear. We are giving a slot from 3:30 to 4:30. We plan to finish the lecture part in the morning half. Only tutorial, maybe you can come a bit late, 3 o'clock. Then you can go for lunch. Means maybe late lunch and late food. Is it okay?
I have an online meeting at 1:15.
Okay.
That means this is not possible.
Yes.
It is?
Yeah, you can have it at 2:30. 2:30 to 2:30.
What can we have?
Your lecture hours. You have an afternoon lecture hour. How do you want to manage? Please let us know.
So normally, today we have it at 3 o'clock. But you said we want to put it in the morning.
No, morning you have other engagement, na? 1:15.
I have 1 hour in the morning and 1 in the afternoon. If you have 1.
Then I'll skip. You take entire morning hour.
Yeah, then I have my